Morning, everyone. Welcome. We're so happy to have you. Today, we are here for the FIRO-MAR workshop. FIRO stands for Forecast Informed Reservoir Operation, MAR being Managed Aquifer Recharge. Let's run through some quick remote participation. First, let me introduce myself. My name is Megan Wiley. I'm with Cal State Sacramento. I'm providing facilitation support for today's workshop. We do have a moderator. I'm going to introduce him in a moment after I run through some virtual housekeeping and a quick fly through of our agenda. So for today, because we do have a large number of folks anticipated to join us this morning around 1:25, we have it set up that everyone is muted upon entry. So thank you very much for accommodating that for us. And we made the decision to primarily use the chat panel for questions and comments. We have a full lineup, and then we will have space to take questions after each of the presentations. And we would like to kind of use a moderated session for that in the way that we would like you all to use the chat panel to submit your comments and questions. And then today's moderator, Duncan Axisa, who just took a sip of coffee, sorry, my timing's terrible. He will be able to pull your questions and comments in from the chat into the discussion session and ask them on your behalf to the presenters. We also have a panel session at the end of today's workshop, starting around 11:25. So some of the more interesting, kind of multifaceted questions that multiple presenters will be able to speak to, Duncan will mark those and he'll bring those into the panel conversation. And we're going to do our best to respond to all the questions and comments, but please know that we might not get to all of them. All of our panelists today, presenters today, are more than happy to follow up with you afterwards. And we have other sessions planned for this year via the FIRO-MAR network. And of course, if they can respond to some of your questions via chat in written form, they'll do that as well. So what's our meeting purpose? The meeting purpose is to figure out what we can learn, what we have learned from this past winter that can improve and inform reservoir operations for future wet years to come and advance FIRO-MAR. Here's a quick peek at our agenda. We will first talk about winter 2022-23 aquifer recharge activity. Then we will look at test sites, specifically Prado Dam. We'll have a little bit of a conversation around decision support tools for FIRO, and then conceptualizing large-scale implementation for FIRO-MAR studies. And then we've got a panel session with all of our presenters. So here's our cast for today. In order of appearance, we have Carrie Talbot with U.S. Army Engineer Research and Development Center, U.S. Army Corps of Engineers. Duncan Axisa, he is with Center for Western Weather and Water Extremes, also known as CW3E, and Scripps Institution of Oceanography. Chad Hecht, also with CW3E. Adam Hutchinson, Orange County Water District. Patrick Singh, U.S. Army Corps of Engineers, San Francisco District. David Arate with California Department of Water Resources, and Wyatt Arnold, also with DWR. We have extensive speaker bios. Extensive, I mean a paragraph per person. I'm going to pop that into the chat so you can all take a little deeper dive on these excellent individuals here to share their knowledge with you today. And before we officially launch, we would love to do a quick poll with you all. Just curious, how familiar are you with FIRO-MAR? We've got a couple of different options here. I'm about to launch the poll, but your options are extremely. If there was a book on FIRO-MAR, I could write it. Or I know my stuff. Let's have a chat by the water cooler. I kind of know FIRO-MAR somewhat, but I'm here to learn more. And then not at all. Isn't FIRO a pizza chain in Texas? So tell us, how familiar are you with FIRO? That's going to help us figure out where to dive deeper into parts of our conversation today. Excellent. Responses are coming in. We'll give you another 5 seconds. We'll close out in 3, 2, 1. All right. We've got one resident expert here. Good percentage of people know their stuff. Most people are here to learn more, and a couple of newbies. So great. Welcome. We're very excited to have you. All right. Without further ado, I would love to welcome Carrie Talbot to give us opening remarks for today's session.
Thank you, Megan. Really appreciate it, and appreciate the opportunity to get us all started here. I do need to say right off from the start that when Duncan Exisa asked me about giving these opening remarks, he prefaced it by saying that Mike Anderson from DWR was not available, and that's really all of our loss. If any of you have ever heard Mike Anderson speak, he's quite entertaining and very knowledgeable. But I'm glad to have this opportunity. I was glad to see that in the responses there that most people have at least some familiarity with what at least FIRO is. Although if there is really a pizza place in Texas, I'm definitely going to try that out sometime. One other thing real quick is that I come from the R&D arm of the Corps. So that's the ERDC is the Engineering Research and Development Center. That's the R&D arm of the Corps of Engineers. And so I've been working with FIRO since about 2014. So this one slide here kind of gives you an overview of what FIRO really is all about, if you don't know. So it's forecast informed reservoir operations, as Megan said. We've been working on this since 2014. And it really is about the R&D to define how forecast information can be implemented safely and effectively in water control manual updates, and therefore practice within the Corps of Engineers. So this really does represent a paradigm shift or a change in how the Corps is managing water going forward, where it makes sense to do so. So we have to assess FIRO viability, and we do that at candidate reservoirs through a very collaborative process. And we test them at so far we've been testing it at reservoirs with a variety of conditions. You can see on the right, these are the current pilot locations within the Corps, but as I'll note here in just a minute, that's growing and expanding because we're now entering phase 3 of FIRO. Phase 1 was testing it initially at the pilot site, which was Lake Mendocino. Phase 2 was expanding that to additional pilots throughout the West, and many of them you see listed there on the right side. Now phase 3 is the national expansion pathfinder. In other words, we're figuring out how to take this across the nation. Some of the results we've seen so far, though, that in a single year, third driest year on record at the time in the Russian River, that FIRO, because we were implementing it there and testing it at Lake Mendocino, there was enough water saved through application of FIRO through a deviation for about 22,000 homes for a year. And we've really had a very minor investment in terms of overall cost, in terms of what this R&D has cost to date, in terms of what the value of the water is. Really, one of the keys, though, that I want to stress here is that collaboration is the key to FIRO's success. Our pilot efforts where we're assessing the viability at a particular reservoir, those are led by interagency steering committees that we carefully form with senior representatives from all of the stakeholder agencies and as well as academic partners. And so we have a blend of engineers and scientists from research, operations, and regulatory perspectives, all working collaboratively on this. So it's not just R&D on one side and then providing a solution that we hope would work to the operational side. The operations side is helping design the viability assessment from the very beginning. They're as invested in it as the R&D is, and that is making sure that what we're producing out of this effort is effective and a viable solution that can be worked both from the research side as well as from the operational side. And these agency logos that I have down here across the bottom, there's sometimes daily interaction going on between all of these groups as we assess FIRO viability at any of these locations. I mentioned that we're now into phase 3 of FIRO, the National Expansion Pathfinder. These are the 6 main elements of that path of what phase 3 will incorporate. I'm not going to go through all of this in detail. We don't have time for that, but I just wanted to mainly point out that we're expanding it using what we call a screening process that was developed as part of phase 2 to look at the entire portfolio of core dams across the country to determine a suitability index for where are the good candidates, where we can do a full deep dive into viability assessments. We're also looking at, as number 3 and number 4 there, you see that there's within the Corps of Engineers portfolio, and certainly other agencies as well, that there are many dams that work together in a system. And so we have to figure out how to apply FIRO into a system of dams. And the Willamette Valley is going to be the first one up for that, with 14 dams being operated all together from a single office. And finally, I just wanted to finish up by talking about the fact that FIRO really is a drought response strategy. Talking about California now, most of the pilots that we've initially started have been in California. Most of the reservoirs, as many of you know, within California either operate within or they contribute to the State Water Project. And every drop that can be made available through FIRO is water that doesn't need to be withdrawn from some other system, for example, in Colorado or some other location. And so pilot studies indicate that the water supply reliability at our pilots can be improved by 5 to 20% with the existing infrastructure at the dam. So we're not talking about adding or changing anything, although there are, some of the pilots do have potential changes, including additional spillways or other structural changes, but those aren't necessarily driven by FIRO. Those were driven from other concerns. And so using the existing infrastructure, FIRO can save up to 20% in terms of making water more available. And so this is an ideally suited mechanism to increase the flexibility of the existing infrastructure to respond to climate variability, extremes, or any other stresses that might come as we move ahead. So with that, Megan, I think I would, and Duncan, I think I'll turn it over to you to get the rest of the workshop going. I'm grateful to have had the opportunity to give just a very quick overview of the FIRO program from the course perspective.
Excellent. Thank you very much, Carrie. Next up, we have Chad Hecht. He'll be speaking to winter 2022-2023 atmospheric river activity. Pardon me, I misspoke earlier. So as Chad's pulling up his presentation, he will be considering during his talk what happened this year with respect to AR activity and how does this compare to an average year. So Chad, when you're ready, floor is yours.
Thank you very much. Everything look good on your end?
Looks great.
Awesome. Yeah, so I'm really here to talk about the past winter we had, which was really quite extraordinary. And my plan is to really dive a little bit deeper and talk and compare it to previous water years. And really the main talking point here is atmospheric rivers. So really what I want to do is start off by talking about what is an atmospheric river. And really, it's just in case some people aren't familiar with what an atmospheric river is, it's exactly what it sounds like. It's instead of a river that's on the ground, it's really just a river that's in the sky. And what it's doing is it's transporting water vapor from the tropical regions where there's a really high concentration of water to the mid latitudes or California, where it tends to be a lot drier. And this is a satellite image where these bright colors are higher concentrations of water in the atmosphere instead of water that's like liquid that's on the ground, like in a river that flows on the ground where it's liquid water. This is just water vapor that's in the atmosphere. And atmospheric rivers are these meteorological phenomena that are transporting this water vapor from the tropics towards California in these long tendril-like features where they run into the mountains of California and force that air to rise, cool, condense, and precipitate. This is a satellite loop from just around the turn of the new year when things just started to get active for California, where we had a lot of these consecutive or the parade or just the punch after punch of atmospheric river that led to a lot of the hydrological impacts that occurred in California. And this is just another graphic that I wanted to present that shows one of the reasons why atmospheric rivers are so important for the hydroclimate of California, where you have the water vapor transport along the coastal range of California, where that moist air is forced to rise and precipitate along the coast, but it also extends inland to the Sierra Nevada, which is on the right-hand portion of this graphic. where the mountains are a lot higher. And then you get also some heavy rain, but also snow as well. And California relies on some of that snow throughout the year for a lot of its water supply. So just diving into what happened this past water year 2023. This is a graphic of each individual atmospheric river that impacted California from October 1st, which is the start of a water year, through March 31st. So the first 6 months of the water year, which tend to be the most active. The summertime, there's not much activity, and there's not much precipitation throughout the Western United States outside of the monsoon. But this water year in particular, there were 31 atmospheric rivers that impacted California. So each individual arrow on this map that you see here is an atmospheric river, and it's placed on the map where that atmospheric river was strongest. And then it's colored based on how strong it was. And the strength of an atmospheric river, usually we use something called integrated vapor transport, which is just a measure of how much moisture is being transported in the atmosphere and in what direction. So where each individual atmospheric river is strongest is where each arrow was placed. You can see there's a lot of activity up in the Pacific Northwest, which is fairly typical. There are a couple of extreme atmospheric rivers, but then we look at California itself. There's many arrows that are pointed directly at the coast of California. In total, there were 31 atmospheric rivers, and 31 is not that abnormal. Typically, from October through March, we see about 33. But the total atmospheric rivers is really doesn't tell the whole story. It's really the quality over the quantity. And this year we saw 6 strong and 1 extreme in this time period. And those tend to be the most productive atmospheric rivers. So we really saw those higher end, those storms that brought really productive precipitation or really high amounts of precipitation to California. Compared to previous years. And in that bottom left panel, you see this is just the total water year to date precipitation from October through March. And you see that we're seeing more than 200% of normal across the Central Coast, extending inland to the Southern Sierra. Northwestern California is right around normal. It tends to be a lot wetter, so you need a lot more storms to really produce an above normal year. And just for reference, water year 2017, which was also a very wet year, I mentioned that this year we saw 7 stronger or greater magnitude atmospheric rivers. In 2017, we saw 13, which is really broke a lot of precipitation records for Northern California. If we really break this year down a little bit further, it was really 2 active stretches. One that started right around Christmas time and then went through mid-January. The active stretch that occurred around the turn of the new year, we saw 9 atmospheric rivers over California that resulted in that onslaught of atmospheric river activity and then precipitation throughout the state. Of those 9 atmospheric rivers, 5 of them were strong or greater magnitude. And I mentioned on the previous slide that California typically sees about 6 strong atmospheric rivers somewhere throughout the state, throughout an entire water year. But in this 3-week period, California saw 5. So to have essentially your water year average within a 3-week period is really just kind of highlights how active that stretch was. And we saw a lot of hydrologic impacts like flooding, but not only flooding, we saw also strong winds that knocked out power throughout the foothills of the Sierra Nevada. And we saw some heavy snowfall throughout some of the higher elevations of not only the Northern Sierra, but also the Southern Sierra as well. And I mentioned on the previous slide as well that water year 2017, we saw 13 strong or greater magnitudes, which is that's the outlier year. But within a 3-week period to see 5 stronger, greater magnitude atmospheric rivers is really extraordinary. And that really kicked off the active water year 2023. And that would have really made the water year. That would have given us an average water year to have that 3-week active stretch. But then we had March of water year 2023, which was another active period, which is really the kind of the bookend of a wet season for California. In total, we saw 7 atmospheric rivers in the month of March, 2 of which were strong or greater. And they were really targeted towards the Central Coast, so Big Sur or the San Francisco Bay Area south, extending inland to the Southern Sierra. The Central Coast of California averages about or less than 1 or 2 strong atmospheric rivers a year. And they had 2 within the month of March by itself. So if we combine the active stretch of December 27th through January 17th, and then you get the active period of March, that's what really drove us to have such an extraordinary wet season this year in water year 2023. And looking at water year 2023, it's really those stronger, greater magnitude atmospheric rivers that result in a wet water year, but there can be moderate atmospheric rivers that are quite productive. This is really comparing this year to the previous 3 water years. And in water year 2020, 2021, and 2022, we had 8 instances of those strong or greater magnitude atmospheric rivers. All of California typically sees 4 or 5 strong or greater. So it's like, we'll call it 6 strong or greater atmospheric rivers in a typical water year. In 3 straight water years, we saw 8. This year alone, we saw 7. And also the base map on these plots here is the percent of normal from October to March. Water year 2020, 2021, and 2022 combined is on the left, and water year 2023 is on the right. You can see there's 200% plus normal precipitation accumulations along the Central Coast, extending inland to the Southern Sierra, central to Southern Sierra, even into Nevada. On the left, it's essentially all orange because the lack of those strong or greater magnitude storms for 3 consecutive years, outside of a couple of really strong events, like the October of 2021 event or 2022 event. Really, one event's not going to really contribute enough to your water year. But this year, we really saw essentially the same amount of storms that we saw over the previous 3 water years. So this water year was really quite impressive. But to dive a little bit deeper, I want to focus on the Central Coast of California, which is like, we'll say Monterey Bay and points south. And this is just the Tulare Basin 6-station precipitation index. From October through March, where at that point in March, we had about 50.6 inches of precipitation, which is right on pace with the year of record, which was 1968, 1969, but also 1982, 1983. I have done this analysis back to 2012, so I can kind of give a little bit of perspective on how abnormal this water year was. So if we dive a little bit deeper, we're going to focus on what the atmospheric rivers from October 1st through April 1st, so just October through March. And if we look at water year 2023, we had 22 total atmospheric rivers that impacted the Central Coast and points southward all the way through the Southern California Bight. But of those 22 atmospheric rivers, 4 were strong. And I want to highlight that the Central Coast to Southern California typically experience less than 2 strong or greater atmospheric rivers each year. And this year we saw 4. But also there were 18 weak or moderate atmospheric rivers that aren't necessarily overly productive, but they do contribute to the overall precipitation accumulation throughout the year. We also have this analysis back in 2019, which is also another active water year. But of those 20 atmospheric rivers that impacted the Central Coast to Southern California, so 20 is more than what we saw this year. But of those 20, only 2 were strong or greater magnitude. So we did get above normal precipitation, but it was not nearly as much as what we saw this year. And then looking at water year 2022, so last year, Again, 2 stronger greater magnitude atmospheric rivers, but there's a little bit of a caveat there. We had a really strong or extreme atmospheric river on October, just about 24th of this water year, but then essentially the tap turned off. And then that second stronger greater atmospheric river was mostly Southern California. It was right around Christmas time, which caused a lot of problems for the Los Angeles basin and even San Diego. So it didn't contribute much to the Tulare Basin 6-station index. But then if we take a look back at some of the other water years, water year 2020, there were 0 stronger greater magnitude atmospheric rivers. And that's where we see 12 inches of total accumulation across those 6 stations in the Tulare Basin. And then looking at water year 2021, again, 0 stronger greater magnitude atmospheric rivers. So if we look at water year 2020 and 2021 for the Central Coast and points south, I know I showed those stronger greater magnitude atmospheric rivers of these years combined on the previous slide. But if we look at just the Central Coast, there are really only 2 of stronger greater atmospheric rivers over the previous 3 years. But they weren't really much of a water supply factor over those 3 years versus this year where we had 4 stronger greater, which is more than double the typical amount of stronger greater atmospheric rivers that we see in a typical water year. And not only that, this year we saw along the Central Coast 11 moderate storms. Typically in a water year, we see about 5.5. So not only did we double the stronger greater magnitude atmospheric rivers, but we doubled those moderate, which aren't necessarily overly productive, but they do contribute to the water supply in this in California. And again, we can break down this water year into 2 really active stretches. The December to January, which started right around Christmas time and went to about mid-January, where we had 7 ARs along the Central Coast, 9 total for California, 2 of which were strong or greater. So we had an average water year in that 3-week stretch for the Central Coast. And then again, we had that another average water year over the Central Coast during March, which really contributed to that, the increase in precipitation accumulation along the Southern Sierra, a place which supplies a lot of California's water supply. But with that being said, every atmospheric river is different and presents its own forecast challenges for California. On the left, I have a loop of that integrated vapor transport, which again is just a measure of how much moisture is moving in the atmosphere and in what direction. So those arrows are identifying which direction it's moving in, and those colors are showing how much moisture is moving in the atmosphere. I want to highlight the difference between that December to mid-January active period and then the late February through March active period. There's a very big difference in the storm track. The left loop here is showing that we really have that direct tap into the tropics, bringing that warm and moist air towards California, hitting the mountains, resulting in that air to rise, cool, condense, and precipitate. And then on the right, there's a little bit of a difference. I'll kind of leave this loop going where the storms are kind of coming from the northwest or the Gulf of Alaska. And in that storm track really leads to a big difference in the temperature. And then I'll kind of throw out these arrows, and that really resulted in a very different storm characteristic between these 2 active periods, where the late December through mid-January, we had your typical atmospheric river type storms, which were much warmer. And then late February through March, with that storm track, it was bringing a lot of that cold air with it. And we had a lot colder storms and snow down to a lot lower elevations, which helped contribute to a larger snowpack throughout California. I mean, we saw snow down to about 1,000 feet during that. But also, I mean, in Southern Sierra, the mountains are high enough to where it really doesn't matter. We saw a big snowpack contribution with that late December through mid-January storm, the active period as well. But I just want to throw up this graphic, which highlights some of the contributions to the snowpack, which broke the 1982-1983 record. In the South, that the warm stretch in late December through mid-January, we see a large contribution to the snowpack in the Southern Sierra, not as much in the north where the mountains are not nearly as high. But in that late February through March, there was a much larger contribution in the Northern Sierra, but again, a contribution in the Southern Sierra where the mountains are a lot higher, which helped to really break the snowpack record. How am I doing on time, Megan?
You're doing well. You have 12 minutes left.
All right, great. One thing that I wanted to highlight about atmospheric rivers before I kind of pass it off to the other speakers in this this workshop is a situational awareness product that we have here at the Center for Western Weather and Water Extremes, which is the atmospheric river scale. The arrow map that I showed on some of the previous slides were really just an instantaneous magnitude of that moisture transport within atmospheric rivers. But we can kind of take that information and use the duration that these storms are impacting the coast of California to really provide some more information about what type of impacts we can expect with each storm. And then also kind of in a retrospective analysis of what we've seen or how strong these storms were. Scales exist across meteorology. I'm sure some of you are familiar with the Saffir-Simpson scale, which categorizes hurricanes on a scale from 1 to 5. The enhanced Fujita scale, which categorizes retrospectively tornadoes based on the damage that they cause. The atmospheric river scale takes into account how long an atmospheric river lasts at a point and how strong it was at that point to categorize these storms on a scale from 1 to 5. So it's very similar to those other meteorological scales, but instead of being event specific, it's point specific. So if we just pick a point along the coast, say San Francisco, we look at how long the storm lasted and how strong it was. So really this slide kind of summarizes that that scale, where if we look at this matrix in the middle here, we have duration on the x-axis and then magnitude on the y. So the longer it lasts and the stronger it was, the higher it is on that scale from 1 to 5. The bottom plot shows how we use this scale in a kind of space. It's instead of being storm specific, it's really point specific. And this was the event back in February of 2017, which resulted in the Oroville Dam incident, where we see atmospheric river 5 conditions along the Northern California coast, which is those red colors. Really, what I wanted to highlight is we have a researcher here at CW3E that did an analysis on the flood damages or the claims, the cost of each event based on atmospheric river scale, and the insurances or the flood damages that were claimed based on the atmospheric river scale. And you can see on the right panel here that as you go up in atmospheric river scale, it's really an exponential relationship with AR5s resulting in a median cost of about 260 million, where the AR1s or the weak to moderate result in $0.1 to $0.4 million of insurance flood claims. So really what this highlights is that those AR1s to 2s are mostly beneficial, but if you go up in the scale, they're mostly hazardous. And that's really what the goal of the atmospheric river scale is to provide that information of, is this atmospheric river going to be mostly beneficial or mostly hazardous? And just to apply the scale to this past winter, this is just a time series of that moisture transport in the atmosphere for San Francisco Bay Area, colored based on what it is on the scale. So those yellows are AR3s, the oranges are AR4s. We don't have an AR5 on this plot, but the blues are AR1s and the greens are AR2s. Just to really highlight how active that 3-week stretch was for Northern California, we kicked it off with an atmospheric river 4, but then followed it up with a couple of 3s and then 2s and then 1s and then another 3 and then another 1. when you really compound these atmospheric rivers from back to back to back to back, that's really going to exacerbate some of your hydrologic impacts, resulting in maybe even more impacts than, say, just an individual AR3 would produce. When you have another AR3 on the doorstep of an initial AR3, you really can produce some additional flooding, and again, an exacerbated hydrologic impact. And this graphic really highlights how active that 3-week stretch was, with the highlighted colors, beginning around 12/27 through January 15th. With that, I'll kind of pass it back to you, Megan. I know we have a panel discussion at the end here, but if there's any questions that I can answer right now, I'm happy to do so.
I'm actually going to pass it over to Duncan, our moderator.
Oh,
We
Duncan.
had a number of questions
sorry.
come through.
Sorry.
Yeah, Chad, thank you for that thorough analysis of the AR activity and the associate strength and impact of those. One quick one is actually from Adam, and it reads, La Nina was the prediction for this year. What changed to produce such an active season?
Oh, that's a great question. Yeah, so if we can look at something like ENSO or El Nino, the Southern Oscillation in the Southern Tropics. Unfortunately, it's not a perfect predictor. And this year we were really we ended up transitioning from a La Nina towards neutral, which seems to be an indication of an active winter for California, because in water year 2017 we had a similar type of signal in El Nino, or the ENSO oscillation, and unfortunately I don't think it really provided enough information about what this winter was going to look like. But I think it's a great learning lesson that we can't just look at one index and kind of hang our hat on it. Every year is going to be different. We can even look back further and see El Niños that were dry or La Niñas that were wet. And this next winter seems like it's going to be an El Nino, which is supposed to tell us that, hey, it's going to be another wet winter. But I'm a meteorologist that likes to look at only 7 days out, and anything can happen any year. And really globally, though, these sea surface temperatures are warm around the globe. So we really haven't seen anything like this. So I don't think we can look at El Nino now and really, I wouldn't bet that it's going to be wet this winter, but it seems to be like it could be. Really, that's the main takeaway there.
Yeah, and also in addition to what Chad said, this is a very active area of research to try and investigate the relationships between these oscillations and the AR activity. I do have one here, Chad, that you could get to quickly. What work is the center doing to evaluate and improve forecast skill, which is critical for FIRO?
There's a lot of research going on there. I don't want to spend too much time on it. One of the biggest projects that we're kind of participating in is something called atmospheric river reconnaissance. California is really in a bit of a tough spot because the weather comes from the west, and to the west of California is the Pacific Ocean, which is a very data sparse region. And if our forecast models don't know what's going on, they're not going to be able to predict what's going to happen very well. And what CW3E is doing in collaboration with a lot of different agencies across the country and even the globe, is using the hurricane hunters that are typically active during the summer months to fly into these atmospheric river storms as they're developing and evolving over the central to eastern Pacific, to go sample and get observations within the storms, take that data, assimilate it into our forecast models to inform the models of what is going on, to hopefully better predict precipitation forecasts over California. And that's really the biggest undertaking during the winter months. And this is just a summary of those flight paths and then the observations that occurred during that active stretch in the first couple of weeks of January, where we had 13 missions with 21 flights and then about 556 drop zones, which is just those, again, the instruments that were dropping from the aircraft through the storm to inform the forecast models what is currently happening. And you can see there's a wide area that these aircraft cover. This is just an image of those planes deploying during January 4th. They're flying towards California. We have the NOAA G4 and then the Air Force C-130s. There's 5 total aircraft from the Air Force and 1 from the National Oceanographic and Atmospheric Administration. And then there's many other projects underway at CW3 that are really the main goal is to improve forecasts, but I'll just mainly highlight atmospheric river reconnaissance.
And maybe a short follow-up on that, Chad. One of the questions is the width of the atmospheric river able to be determined before arriving at the coast? And this seems to be lining up what you have here.
Yeah, I mean, that's the goal, right? You want to perfectly predict it, and that's one of the main forecast challenges is identifying the exact characteristic of every individual storm. If it's wider than what you anticipated, then you're going to have more widespread impacts. If it's narrower, maybe it's going to target one watershed versus another. If it's shifted further north, it's going to cause more problems, or if it's shifted any direction, it's going to cause problems over a watershed that maybe you didn't expect. And this winter gave us every possible challenge that you could see within individual atmospheric rivers. We saw flooding in one watershed and not another because one atmospheric river decided to stall. The width of an atmospheric river is a very important characteristic that we really need to forecast or nail down prior to it making landfall. And I think that's a great question that highlights some of those challenges.
Yeah, essentially the measurements that we're doing here are done across the width of the atmospheric river.
Oh yeah.
At 4 or 5 days ahead of them making landfall, and that data goes in the model, which is improving how that atmospheric river dynamics, the size of it, the length of it, the amount of water vapor, those properties are better predicted. I think we're up on our time, Megan, so I'll give it back to you.
Thanks, Duncan. Thank you very much, Chad. We have a number of questions that we're saving for the panel discussion. But next up, we have Adam Hutchinson with Orange County Water District. Adam, when you're bringing up your slides, let folks know. So Adam's going to be talking about how did FIRO make a difference in managing runoff in 2022-23, and what were some lessons learned from this year? And I'm going to pop in the speaker bios in the chat panel one more time because we got a number of folks who joined, I think, after I shared that document. Adam, when you're ready, take it away.
Hey, good morning, everybody. It's great to be here with all of you. Let me pull up my presentation here and we'll get it going. Thank you. So I'm here to talk about the FIRO at Prado Dam. As Carrie mentioned, there's different pilot locations in California, and we are the second one. Lake Mendocino was the first. We're happy to follow in their footsteps and start this project. And so we're excited to present some results of analysis that we've done, but also talk a little bit about this year and what happened. As Chad mentioned, it was an extraordinary year. So we've got some interesting results to share with the group. And there's a lot of great potential for FIRO to benefit our area as well as other areas in the state of California. So just to orient you where Prado Dam is located, the red star in this figure is located at the intersection of Riverside County, San Bernardino County, and Orange County in Southern California. And Prado Dam is basically capturing water from the upper Santa Ana River watershed. The Santa Ana River is the longest coastal river in Southern California, originating up in Big Bear in the mountains and draining to the Pacific Ocean. We're very fortunate in Orange County that we're immediately downstream of Prado Dam. So we have the benefit of capturing water from the upper watershed and then taking that water and recharging it into the groundwater basin. So the gist of it is doing stormwater capture at Prado Dam. And then that water that is captured is then recharged into the groundwater basin for later use. So classic conjunctive use where you're capturing water during the wet times and saving it in the basin for the dry time. And with the changing climate and the climate whiplash that we hear so much about, it's really critical for resilient water supplies for Orange County. So here's a photograph of Prado Dam. It was built in 1941. Recently, the Corps of Engineers has improved this dam. They've raised the dam 20 feet, put in new outlet works that have tripled the capacity of the dam to let water out. And the spillway there that you see in the figure is under design, and it will also be rebuilt here in the near future. And the one thing I wanted to mention in this photograph is what you see behind the dam is a very large riparian forest, one of the largest in Southern California. Very valuable habitat for endangered species, primarily the least-billed vireo. And so this has a very extreme environmental benefit to the region. And that's one of the things that we have to carefully manage as we implement FIRO at Prado Dam. And also, you can see in the top of the figure, these ponds, those are our constructed wetlands that OCWD manages. We have hundreds of acres of constructed wetlands to treat water that comes down in the Santa Ana River. So we're actively managing this area for environmental benefits and water quality benefits. So water conservation behind Prado Dam is not something new. We've been working with the Corps for many, many years, going back to the early 1960s. And this figure here schematically shows the changes that we've made over the years in increasing the amount of water we can hold behind Prado Dam, whether it be in the flood season or non-flood season. And the most recent increase is happening in 2021 at the purple line, where we can hold water up to elevation 505 year round. And that represents about 20,000 acre feet of storage. Now, this is different than other core dams. This is a dry dam, and so there's no permanent water held behind the dam year round. It's dry, like right now, there's no water behind the dam. But during the winter time, the Corps can temporarily impound the water up to that elevation and then release it downstream to us in a manner that we can take that water and capture it and recharge it into the groundwater basin. And of course, FIRO is the newest evolution of the development of this water conservation program. And so it's still to be determined how high we can hold that water. And of course, with FIRO, that might change in the future as our forecast ability improves and gets better. So here's a figure showing our recharge system downstream of Prado Dam. It's a very large, complex system that's been built over the last 90 years, covers over 1,500 acres of land, 26,000 acre feet of storage. So this is where the magic happens. Once that stormwater is released from Prado Dam, we divert it into these recharge facilities and sink it into the aquifer. And I'll note at the bottom of the figure, you can see there the tour being scheduled for September 19th through the FIRO-MAR work group. And Megan will put a link in the chat to sign up for this event. It's limited to 24 people. If you want to come, be sure to register right away. Be happy to show you this system in person, up close. So this pie chart here shows you our water supply portfolio in Orange County. You can see it's a pretty diverse portfolio. Our average water demands right now are approximately 400,000 acre feet per year. And this pie chart kind of shows what are the different sources of water we use to meet those demands. And right now, the largest source obviously is recycled water there through our groundwater retention system, which just was expanded to 130 MGD this year. You can see that is the largest supply we have. But storm flow is an important supply and imported water as well. And what is important about FIRO is if we can increase storm flow, every acre foot of storm flow we capture is directly offset 1 acre foot of storm water that we need to import to satisfy our water demand. And that's really critical now because there's no imported water supplies in Colorado River and Northern California are becoming more under stress and increasingly less reliable. But stormwater is a local supply. It's right here in our region. It's less expensive and has a much lower carbon footprint compared to imported water supplies. So that's really the driver behind stormwater capture, is really offsetting imported water in the region. So what is FIRO? Well, we've kind of gone over this, but for Prado Dam, it's the objective here is to optimize flood risk management, water conservation, and environmental benefits all together, finding that win-win for all three of those. In our case, without pouring a yard of concrete, so it's really optimizing an existing infrastructure for the modern era that we're in right now with climate change, as well as new technology and new information. How can we really better utilize an existing facility with what we know now? So it's complicated. It's not easy. As I mentioned, there's a lot of different factors that we need to balance as we implement FIRO at Prado Dam. I mentioned the least Belverio, there's land and infrastructure in the basin, roads, airports. There's that large riparian forest that we have behind Prado, and what are the potential impacts to that forest or benefits of FIRO in terms of providing water to that habitat. There's weather forecast skill. How good are we at assessing storms and their intensity? And the release rate downstream of the dam. We want to be mindful of how much water we release and what kind of flow rate, so we don't damage any infrastructure downstream. And of course, at the top, the primary purpose of the dam is flood risk management. So whatever we do, we need to make sure we don't compromise in any way the flood risk management function of the dam. That's primary in all FIRO cases. There's no different here. So because it is so complicated, as Carrie mentioned, we have a very stakeholder-driven steering committee process that we put in place. It's called the viability assessment process. There's multiple phases. We started this back in 2017, and today we are near the final stages of our final viability assessment, where that's going to be published later this year. And that's kind of the final document that shows what is possible for FIRO at Prado Dam. And we're also going to do what's called a minor deviation at Prado Dam, where we're going to hold the water at higher elevation on a temporary basis for 5 years. And test FIRO, test the different mechanisms and data tools we have to manage the reservoir and see how much more yield we can get, what kind of impact we can see. And of course, the ultimate objective is to make a permanent feature of Prado Dam by updating the water control manual. So a lot there. We learned a lot through this process. It's very important to go through the process. Even though we thought we knew what might occur, we were very surprised at something we didn't know. And so very important process to go through. So on to this year, Chad showed this diagram already. We had a very active season. It was no different in Southern California. We had a lot of atmospheric rivers hit us in Southern California, which was very beneficial. And it wasn't a record-breaking wet year, but it was definitely almost 200% of average, like Chad mentioned. 2004, 2005 was a record year in our watershed. But we did have above average rainfall, so that was very beneficial. But what I think is very instructive is it wasn't the total amount of rainfall that we had, but it was how the rain came. And as Chad mentioned, we had kind of those two active seasons, one in January, one a little bit later. And that was true in Southern California. The rainfall was really spread out over a long period of time. And that's evident on this figure here. And what this figure shows is the water level behind Prado Dam over the course of our water year from July to June. So the yellow line shows the water level. The red line is the maximum level that we can retain water behind the dam. So you can see we had storms starting in November, extending all the way through May of this year. So an extremely long time frame, unusually long for our area to receive rainfall. And this was ideal from a water conservation perspective. You can see in January, the water conservation pool filled up, and then the drier February allowed us to drain that pool and create more space for future storms. And even in May, we were able to get a bump in that conservation pool as well. So really ideal, keeping that pool full, allowing periods of time for us to drain it and refill that pool again. And one thing I want to highlight before I leave this figure is you can see that the core, using forecast information, will allow that water level to go above the limit of 505 because we have confidence in knowing what's coming ahead. And so they would allow the water level to go above 505 and then quickly drain it down in a safe fashion down to the target level. And so that's been the benefit of this process, is giving the Corps more information, more collaboration, more flexible use of the flood risk management space above 505. So a great partnership with the Corps. Really appreciate their efforts and all the hard work they did to manage this pool this year. And as a result of this ideal winter that we had a very exceptional amount of recharge that we were able to accomplish this year, a higher amount than we've been able to do for many, many years. So an exceptional year for rainfall and particularly for recharge. So spacing of the storms is really important. So just a reminder that it's not the total amount of rainfall, it's really how it falls and when it falls. It is really critical to FIRO and manufacturing recharge. And this graphic here is similar to what I showed earlier, the level behind Prado, going back 6 years. And what this really shows is that because of conditions in Southern California and maybe even the climate whiplash that we're seeing, we only get enough water to fill the conservation pool on average every other year. And intervening years are very dry or less wet. And so FIRO is really an opportunity for us to maximize those wet years when they do occur and make sure we can capture what we can and bank it for those dry years that we know are coming. So like Carrie said, it's really a drought response tool. And this figure here shows that we're only going to get enough water to fill the pool every other year. So we really need to make the most of it to maximize what we can get. Now, one thing we did this year that was pretty interesting is the CW3D staff set up a virtual operations model. So think of it like AI for FIRO. Basically, what it is setting up a model that uses the forecast information being generated by the California Nevada River Forecast Center and taking that information and sticking it into a model and saying, if the model were to operate Prado Reservoir, what would it do? And you give it some constraints and some boundary conditions, but just let the model take the forecast and run with it. And in this case, what we did was set it up for 508. That's the elevation we want to take it to in the coming winter. So the blue line shows the virtual model that was set up and how it would operate the reservoir without human intervention. We just set the rule and let it run. And the black line shows how it was actually operated by the Corps of Engineers. And the thing I want to bring to your attention is really how those lines are pretty parallel to each other. They show that the model and the Corps operated in a pretty similar basis. So it's just an instructive tool that we're putting together to give the Corps another tool in the toolkit to kind of look at what would the model do if we were just using forecast and taking them and at face value and implementing decisions based on the forecast. And so this is a tool that we can continue to develop and make available to the Corps as the years go on and see what kind of value it brings. One thing I want to bring to your attention, we did have a false alarm in January, and that's shown in the red circle here. And what happened there was the forecast that came in was such that the model said we need to release water in advance of this very high storm event coming, or a lot of volume coming into the reservoir. And so the model released that water. The Corps did not. And so I want to share a little bit of information on what happened with that storm event. But I think it's pretty instructive for us, particularly in our watershed. So this figure, you've seen it before, showed the Santa Ana River watershed, but also extends to the west, showing areas in LA County. And I'm going to show you some data from Prado Dam, but also Hansen Dam in LA County in the upper left-hand figure there. So the graphic here shows the forecast from the California River Forecast Center, showing what was forecast coming to Hansen Dam back in January of this year. And so the black line that you see right here is the official forecast, the median of all of the envelope of ensemble members that were run for these models. So the Forecast Center generates these ensembles and kind of puts percentages of exceedance on those. And so basically the deterministic model is kind of in the middle of all of these. So that's what was forecast. But what actually happened was what this red line, it actually exceeded even the probability, the highest probabilities were exceeded. And the inflow was, many, many times higher than what was forecast for LA County. Now, this is the forecast for Prado Dam. It also showed a very high potential forecast. You can see up to 40,000 cubic feet per second coming in. Black line is what was the deterministic value, and the blue line is what actually happened. So it's almost a flip-flop where for Hansen Dam, you had a value that exceeded even the highest probability of exceedance, and then in Prado, it actually went below the lowest probability of exceedance. So it's interesting, it really showed that there was a forecast error here, and we're going to be using this as a case study to dive into what was some of the reasons why these forecasts were so inaccurate. But it also provides information for the Corps in the future. When looking at these big storm events, we need to be really careful about responding to them and monitoring these forecasts as they occur, and look at the changes that might happen as the storms progress, take action accordingly. So we learn a lot from these kind of events, and we're certainly learning more every year. So as I mentioned, we're almost done with the FIRO final viability assessment. And this figure here kind of shows the different estimates of increased recharge we might achieve, depending on the higher elevation that we can store water behind the reservoir. And so, we're ranging anywhere from 2,000 up to 12,000 feet per year of additional recharge, depending on the elevation. 520 is probably a little higher than we would ever want to go, but some of these lower elevations are going to be targets for FIRO going forward. And so this is showing extremely high benefits for the region. As I mentioned, every acre foot of stormwater we capture is an acre foot of imported water we don't need to bring into the region. We're very excited for the opportunity to capture more water behind Prado Dam. So to wrap up, I thought I'd just show you a few photographs from this year. This figure here is looking to the east. Prado Dam is off the figure, but kind of showing the arrow there. It's up with the county line on the top of the figure. And you're looking at the Santa Ana River on the right, and our big Warner Basin in the foreground right there. It holds a lot of water. So everything's full here in April. We're still draining the pool during this figure. Here's a picture of our Anaheim Lake, and the watercolor you'll note is very blue because we're actually taking imported water at this time from the Colorado River, so I have a nice blue color. And in April, here's a picture of Anaheim and other basins in the foreground there that are full of stormwater. As a result of Prado Dam releases. And then finally here is Santiago Basin. It's a former gravel pit that we converted to a recharge basin. You can see it's very steep wall basin, a lot of storage, high percolation rate when it's full, and it's full. So we were able to really recharge a lot of water in all of our facilities this year, as I mentioned earlier. So as I wrap up the presentation, just want to note that, FIRO is going to make a huge difference at Prado Dam. FIRO is not officially in place at Prado Dam yet, but forecast information is and has been used in the past and will continue to be used in the future. These tools that we're developing, like the virtual model I mentioned, and other tools that CW3D is creating in the core, are being developed and are being improved over time and are really going to make a big difference. And so our forecast skill is improving. As Chad mentioned, we're doing observations off the coast and continuing to collect a lot of great information, and that's going to make our forecast even better going forward. And forecasting, better tools, everything at FIRO is going to get smarter and better every year as we go forward. So as I wrap up, stormwater capture is extremely valuable for Orange County. For local supply, if conjunctively used, we're going to put that water in the ground and save it for dry years. The cost is extremely low compared to imported water with a much lower carbon footprint. And it's got the potential to improve habitat health in the Prado Basin. As things get drier and hotter, these opportunities to capture water during the wet years are going to really benefit the habitat behind Prado and provide benefits to the habitat and the environment in general. So that is my final slide. So happy to take any questions if there are any.
Thanks, Adam. FIRO at Prado Dam, the assessment has been going on for several years now, and it has matured a lot, and there's findings that are encouraging and beneficial for the watershed and for Orange County. What are the biggest hurdles in implementing FIRO at Prado Dam? So now going from the assessment where the feasibility is being studied to implementation, what would be the biggest hurdles with that?
Yeah, that's a great question. I think there's two of them. The primary hurdle that we need to get over is really understanding the impact to the environment behind Prado Dam. There's very little understanding of the effects of prolonged inundation. When you capture water at a higher level, it takes us longer to drain that water out because our recharge capacity is fixed. And so we're very concerned about the additional days of inundation that the vegetation will be impacted or subjected to. So it's an area of research and learning. And we're really pleased through the stakeholder process. We really generated some good relationships with the U.S. Fish and Wildlife Service. And so I think we've all come to understand that the FIRO has potential benefits, but potential impacts as well. How can we collaborate and work together to really make sure we study the impact together and the benefits and make decisions accordingly, like an adaptive management plan as you go along versus trying to understand all the impacts up front because we don't know enough. And so I think we've really come a long way in pursuing developing an adaptive management plan and approach, a cooperative approach with Fish and Wildlife to study the impacts and benefits. So that's the biggest hurdle right there. I think the second hurdle is just developing really good tools for the Corps that they can use to make decisions. And that's an area that we're going to really work hard on in the next 2 or 3 years. I think from here at Prado is seeing what tools are the most effective and provide them the best information. And our forecast gets better, get better, our skill gets better. That's going to really make a big difference for them.
Thank you, Adam. there's a question in the chat here that I think we can take now. Is there coordinated FIRO operation with Seven Oaks Dam?
Yeah, that's a good question. The Seven Oaks FIRO effort had just started. They just had their kickoff meeting about a month ago. So they are going to be studying FIRO at Seven Oaks. And so definitely in that process, we're going to be working on coordinating and seeing what kind of mutual benefits can be achieved by doing FIRO at both Prado and Seven Oaks. So more to come on that. I'm sure that'll be a subject of a future presentation.
Okay, and we have time for another one. So we've talked about FIRO at Prado Dam, and we're going to also hear about FIRO at Lake Mendocino, and Kerry touched on the transferability of FIRO. And based on your experience with FIRO, Adam, what advice would you give to others contemplating either studying or using forecasts for reservoir operations?
Great question. Like I mentioned earlier, the CW3E has a very, and the Corps have a really good viability assessment process that's been curated over the past few projects, like Mendocino, Prado, and others. And, going into it, I wasn't sure what it was going to show us, but it really did show that you need to go through this process, and it involves all the stakeholders that are involved. In our case, it was the Corps, U.S. Fish and Wildlife, the Orange County, Department of Water Resources, just trying to bring everybody to the table, because you learn so much more, you get buy-in, and everybody can see the benefits of FIRO. So I think the viability assessment process is critical, and also making sure you have every stakeholder possible at the table involved in the process. I think those two are the key components.
Excellent, thanks, Adam. And I think we have time for this one as well. Have there been any particular hurdles with recharging to groundwater, perhaps with groundwater compatibility or infrastructure management?
Yes, so the primary constraint to recharge for us in Orange County is clogging caused by suspended sediment in the water. So during the storm season, at the beginning of the season, our recharge capacity is very high because everything's clean and ready to go. But as the season progresses in stormwater, we call it chocolate milk here, when it's really turbid and the high flow rates are high, that chocolate milk can really clog our recharge facilities pretty quickly. And so our recharge rates can decline by as much as 50% or more as the season progresses. So it gets harder for us to recharge water later in the season. And so one of the primary constraints is clogging. We're trying to develop some innovative methods to deal with that clogging, and that's another discussion for another time. But that's really the primary driver for trying to improve our stormwater capture, is reducing clogging.
Thank you, Adam. And we're up on our time for this part, but if there's other questions, please put them in the chat, and I'm keeping track of those, and we'll have them in the panel. So back to you, Megan.
Adam, thank you so much. So we have two presenters left, then a panel discussion. I just wanted to note we plan to take a short break at 10:45 following Patrick's presentation. And by short, I mean 5 to 7 minutes. So stretch if you need it. But we're excited to welcome next Patrick Singh to talk about FIRO decision support tools that are available for reservoir operators to make forecast-informed decisions, and how these tools could be used to advance FIRO and FIRO-MAR throughout the state. Patrick, when you're ready.
Thank you, Megan. Just doing a sound check. Can you hear me okay?
You sound wonderful.
Okay, let me share my screen, and Megan, if you can also confirm that the screen is shown, and then I'll get started.
Looks great.
Okay. Well, thank you. I appreciate the opportunity to talk to you all today about the real-time use of FIRO decision support tools at Lake Mendocino in the current water year. I'm Patrick Singh, the lead water manager from the Corps of Engineers, San Francisco District. We just heard a talk from Adam about the virtual simulations of FIRO at Prado and what may come in coming years in terms of real-time implementation there. It's a good transition to my presentation because we've gone from virtual simulations to actual application of FIRO. So I'm going to share with you how that occurred this water year. So Lake Mendocino is one of two major reservoirs located within the Russian River watershed. This is a watershed that is approximately 1,500 square miles in size. It contains both Mendocino and Sonoma counties, and this overall watershed is located north of the city of San Francisco in the great state of California. So reservoir releases out of Lake Mendocino are based on rules prescribed by the Water Control Plan. That Water Control Plan was originally written in 1959 and received a minor administrative update in 1986. And in this Water Control Plan, there's a designated boundary between a water supply space and flood control space. Within that water supply space, storage can be held indefinitely, so that can be used for drinking water, irrigation, and recreation purposes. And then the flood control space, which is above the water supply space, that is only allowed for temporary storage. So that was designed to allow for rainfall runoff to occur. The reservoir captures that storage, and then when conditions are safe downstream, we release that water. This is a little bit different than the Prado Dam example, where that dam is typically empty. This reservoir typically has water in it at all times. It's just a matter of how much water is in there. There are no rules for snowmelt at this reservoir because there is usually no snow in the watershed. This is actually pretty atypical of a lot of reservoirs in California. So when you think of reservoirs like Lake Oroville, Folsom Lake, those reservoirs experience a lot of snowmelt in the spring and early summer. Here, we don't experience that. So really, our major inflow into Lake Mendocino is only during the winter months. So here, this is a graphical depiction of the water control plan for Lake Mendocino. So for your reference, on the bottom, you'll see a time scale starting October 1, going to about July on the bottom. The orange line is the boundary between the water supply space and the flood control space. And the red line is the overall capacity of the reservoir. So you'll notice that the water supply space is smaller during the winter months and larger during the summer months. That's because we expect the most rainfall runoff to occur in the winter as opposed to the summer. So therefore, we need a bigger flood control space during the winter months. So water managers like myself, we can operate differently than the rules prescribed in the water control plan if there is a deviation requested and then subsequently approved by the Corps of Engineers. So a reason for why a deviation may be requested, there could be lots of reasons. For example, if there's planned construction at the reservoir that can affect how we release water, that could be one reason that a deviation may be requested. Drought conditions in the watershed could be another reason that a deviation is requested, and so forth. Before a deviation is approved by the Corps, it has to undergo rigorous environmental, engineering, and dam safety review. So Sonoma Water, which is the local non-federal sponsor of Lake Mendocino, and also the agency that manages the water supply space, they have actually submitted various deviation requests over the last few years, and we've actually approved those deviation requests. So there was a request made in 2019, 2020, and for the current 5-year period of 2021 through 2026, and those requests were approved. And the reason for that request from Sonoma Water was to respond to ongoing drought in the Russian River watershed, but it was also so that we can evaluate and test, forecast, and inform reservoir operations in real time. And the motivation to evaluate and test FIRO was because of a viability assessment report that was completed in 2020. So there is a fully published report available out there for the public that describes how FIRO was tested in the virtual sense and how it is viable potentially in real time. And that's what we're trying to do right now through these temporary deviations. So that image or that diagram that I showed you earlier now has been modified. I've added a gray line. That shows you the boundary of storage that we're working with deviation. So it's important to note that the orange line, which is the boundary between the flood control space and the water supply space, does not change even with this deviation in place. What has changed is there is that boundary between the orange line and the gray line where forecast informed reservoir operations is allowed. So there, the water manager, which in this case is myself, can selectively retain or release water based on forecast information. Any storage above that gray line is still the normal flood control space where storage must be temporary. So as rainfall runoff occurs, any storage that reaches above that gray line must be released once conditions are safe downstream. That's consistent with the existing water control plan. However, any storage within the orange, between the orange line and the gray line, that is at the discretion of the water manager to retain or release. So this was an image that you might have seen during the first presentation of this meeting. Carrie showed this image. This was an image that I took of the lake and the embankment when I visited the lake in January 17th. So it's a very visibly full lake. And of course, that's in contrast to Governor Newsom's visit in 2021, where he was standing on the lake bed of Lake Mendocino, giving a talk about drought. It's safe to say that 2023 has seen a significant change of conditions of Lake Mendocino. And this graph will visually illustrate that change in storage. So the orange line, again, is the boundary between water supply and flood control. The gray line is the top of allowable FIRO space. And then the red line is the capacity of the reservoir. So you'll notice that we came into this water year with a really low storage, and that's that blue solid line. These blue bars at histogram type of image is actually cumulative precipitation. So you'll notice for the first few months of this water year, we had some precipitation, but then we had that significant jump in precipitation from December to January, which caused a significant rise in storage of the reservoir. When the reservoir exceeded that gray line and we were within the flood control space, water was released as required. And then we had to evaluate a question, which is, now we're approaching this FIRO space. What do we do? So now I'm going to talk about what we did do and how we applied our FIRO decision tools in our decision making. So I'm going to go over decisions that were made from January 25th to February. That's going to be the first part of the upcoming slides. And then I'm going to talk about early March. So January 25th through February, the Corps decided to maintain the reservoir storage near the top of that FIRO space. We go back to the previous slide, you look at that blue observed line for storage. We were maintaining close to that threshold that's allowed for FIRO space. We made this decision to maintain that storage due to the direct application of quantitative and qualitative assessments available through these FIRO tools. And I'm going to go through the three tools that our staff was using quite a lot this water year. So here you see an example of the reservoir cumulative inflow volume forecast from January 25th. This is a direct output of the hydrologic ensemble forecast system, shorthand known as the HEFS, that is run by the California Nevada River Forecast Center. So the ensemble runs are supposed to give a range of possible cumulative reservoir inflow. The dots represent a % chance based on the ensemble runs. A red dot represents a higher probability, while the blue dot represents a lower probability. Here you can see on January 25th, the majority of the ensemble runs were in agreement that the cumulative inflow would be minimal. So if you look at that 5-day cumulative inflow from about January 25th to January 30th, the cumulative inflow was ranging from 2,000 to 3,000 acre feet of inflow. For some context, we were releasing about 3,000 acre feet of water over that same 5-day period. So basically the forecast was indicating that our storage overall change was going to be 0. With this forecast of minimal inflow, this was a tool that helped support our decision to maintain the storage of the reservoir near the top of that FIRO space instead of releasing. Again, this is just one tool available that we used. So here's an example plot of the forecasted probability of landfall on the west coast of California of integrated vapor transport, also known as IVT, of greater than 250 kilograms per meter second from the Global Ensemble Forecast System, also known as the GEFS. This is the meteorologic model that is used by the River Forecast Center. Again, this product is from January 25th. More purple on this image means that there are more ensemble members that indicate landfall of IVT greater than 250 kilograms per meter second. That 250 kilograms per meter second is a key number. This was a number that was studied and developed by the Center for Western Weather and Water Extremes, and they found that IVT greater than 250 kilograms per meter second is what typically produces the precipitation that can lead to rainfall runoff. So here you can see that from the period of January 25th to about the end of the month, that 0 to 9 number on the bottom axis, you'll notice that there aren't any atmospheric rivers forecasted for that period. It looks like there was some potential small chance beyond February, but for the near term, about a week, there was no forecasted atmospheric rivers. This again was a product that helps support the Corps' decision to maintain the storage within that FIRO space instead of releasing the water. Finally, a third plot. Here, this is the plot of forecasted range of values of IVT specific to 39 degrees north, the location of the Russian River. Note that the previous plot was the probability of IVT exceeding 250 kilograms per meter second for all of California. Here, this is looking at the actual IVT value forecasted for this location. Here you can see IVT was forecasted to be low. In fact, it was forecasted to be below 250 kilograms per meter second for about 16 days. This again was a tool that helped support our decision in the Corps to maintain the storage at that FIRO space level. I've gone through 3 tools that I thought was useful. These weren't the only tools that were used, but I just wanted to illustrate to you all how these tools help support our decision to maintain the storage instead of releasing the water. Now we're going to transition to early March, where the Corps actually did decide to make a release and not keep storage near that gray line. So let's talk about early March. So here, I'm going to go through the same 3 products that I showed you earlier, but with different results. So here, this is a product available on March 7th. And unlike January 25th, where you had agreement on the ensemble runs, which was low inflow, now you can see a wider range of ensemble runs and much more inflow. In fact, you'll see over this 10-day period, there is the potential for inflow to range from 10,000 to about 35,000 acre feet. So it was clear in early March that there was going to be wet weather that would increase reservoir inflow for Lake Mendocino and would necessitate the need for the Corps to start evacuating some of that space instead of keeping it to the top of the FIRO space. Again, we're going to show you the atmospheric river landfall tool for IVT greater than 250. Unlike the example I showed you in January, now you're seeing a lot of red and purple, which is high probability of an atmospheric river approaching the California coast. This again was used to support our decision to release water. And then finally, this is the IVT forecast specific to 39 degrees north location of the Russian River watershed. And you'll notice that the IVT range was forecasted to well exceed 250 and even get up to potentially 750 kilograms per meter second in that early March period. And again, a tool that helps support our decision to not maintain the storage near the top of that FIRO space of Lake Mendocino. So what was the overall outcome of Lake Mendocino in terms of the flood season? Well, FIRO was functional at Lake Mendocino. We were able to use those tools. We were able to process those tools, and we made sure that we did not make any reservoir releases that contributed to flooding downstream. So in other words, as conditions were high downstream due to natural rainfall runoff, we did not release any water, and that was the result of using our tools with FIRO. So there was slight exceedance of flood stage in the upper watershed at Hopland, shown on the left, designated by that red line. There was no exceedance of flood stage in the lower watershed, shown at right, again with the red line. Again, I want to emphasize that these flows, as they got close to that red line, that was due to just natural rainfall runoff. That wasn't due to any reservoir release that was made at Lake Mendocino. Although I focused on how we applied FIRO at Lake Mendocino, and that was the title of my talk, I did also want to give a short plug to Lake Sonoma, which is the other reservoir in the Russian River watershed. This was the first year that we started to attempt to apply FIRO there through a temporary deviation. The graph that you see on the screen is different in terms of Lake Mendocino versus Lake Sonoma. So here you'll see that at Lake Sonoma, the boundary between the flood control space and the water supply space is actually flat for the entire year at 245,000 acre feet. The gray line is supposed to represent the deviation that we have in place at Lake Sonoma. And here you can see, because of that deviation at Lake Sonoma, we were able to actually retain a significant amount of water there. So after the storms that occurred in March, instead of bringing the reservoir at Lake Sonoma back down to that orange line, which is 245,000 acre feet, we were able to maintain the reservoir at 264,000 acre feet. And we were able to maintain that for some period of time until water had to be released to meet the minimum inflow, to meet the minimum in-stream flow requirement downstream. But at Lake Sonoma, application of FIRO there has resulted in 19,000 acre feet being retained instead of released. And that I'm sure that's a valuable amount of water given potential drought conditions that may follow in the years to come. So how is the San Francisco district going to maintain and advance the use of the tools that I showed you today? Well, I can tell you that existing San Francisco district water management staff, that includes myself, we have to regularly check these outputs in the morning, afternoon, and evening each day during the flood season. And we're going to have to ensure that future water management staff receive training to do this. It's really important to note that these outputs can change unexpectedly from one forecast period to another. So you may look at a forecast product in the morning, and then you transition to the afternoon and evening, and there could be a change. So it's really important for water managers to closely track that, because if there is any significant changes in forecast, we need to adjust our operations accordingly. The other important thing that we did this year and recently is we've established lines of communication with subject matter experts regarding the outputs of the tools that I showed you, to ensure that water managers like myself properly interpret those outputs. And it's going to be important that we continue to maintain or even enhance those lines of communications in the years to come. I had the pleasure of communicating with several folks at the National Weather Service, notably Brett Whiten, on numerous occasions during this water year, just to double check what we were seeing from these outputs. I also had the chance to speak with Chad, one of our previous presenters from the Center for Western Weather and Water Extremes, to get his perspective on what these outputs were showing. It's important for a water manager like myself not to pretend that I'm an expert meteorologist or an expert in how these products are produced. We need to talk to the smart people who could really give us the answers that can then inform the water management decisions that we need to make at our lakes. What also was important this year for the water management staff at our district and even our leadership, that includes our commander, was to establish lines of communication with the community so that they're aware of how we're applying FIRO in real time. Lake Mendocino was constructed in 1959 and was operating to a certain way for decades. So as we're trying to implement FIRO and we're changing the way we operate, it's important that we communicate with the community how we're changing our operations, because the people in the community are monitoring what happens out of the lake. And if we do things differently, it's going to be important for them to know why we're doing things differently and that they have confidence in our decisions. The last thing we want to do is create a panic in the community because we're operating differently and they don't understand why. So with that, that concludes my presentation. I know we have a chance to talk with questions right now. In case you're shy and don't want to ask a question in the chat or through the panel, you can feel free to email me. But with that, I'll take any questions that we may be able to answer right now with the time remaining in my speaking spot.
Thank you, Patrick. We do have one question that is interesting, and it may require others to pitch in. And that states as follows. These presentations focus on using FIRO to respond to weather changes. What about using FIRO to adjust for changes in downstream accommodation, absorption of higher flood flows during an AR event? And I think this points to some of the modeling, Patrick, where the downstream conditions are actually being monitored. Can you take this at least in part?
Yeah, I mean, if there's any changes in downstream control in terms of assumptions of what's allowed or what can be manageable, I think you're going to have to start off with some numerical modeling to see in a virtual space what impact that would have on reservoir operations. And after you've thoroughly done that, then I think you can evaluate how that gets applied in real time through deviations. that's, I think, really a general answer to that question. If there's any others on the panel that want to chime in, they can, but that's how I would approach it if we were faced with that situation in San Francisco.
Yeah, I'll mention something. So the downstream constraint isn't so much driven by the absorption capacity of the Santa Ana River, but more by our diversion capacity. We have 2 rubber dams that divert water off the river into our recharge system. And if the flow exceeds 1,000 CFS, those rubber dams have to be deflated. And so I think FIRO provides an opportunity for us to kind of modulate the outflow rates so that we can continue to capture water, but also protect the flood risk management of the dam. And so that's really where the downstream flow component impacts OCWD. So it is an important component. I know for Patrick, you're more concerned about actual flooding of downstream community. In our case, the constraint is more our diversion capacity and trying to manage to that.
Maybe I'll add a little bit on that, and I'm not an expert on this, but we do implement models that are incorporating the ensemble forecast of inflows and monitoring the downstream flow requirements and the flow control points downstream to manage the water supply for either flood or storage. And there's a formulaic way that's done depending on the objectives of operating that reservoir. So I think the whole point, as Kerry would put it, and I know Kerry can comment here, but Kerry would say it's about flexibility. So how can we better operate the reservoir to better manage the objectives in a flexible manner by utilizing an improved forecast and also improved monitoring in the watershed.
Yeah, I'll just chime in real quick here. Duncan, you're exactly right. Whatever those objectives might be, we've been looking at 2 reservoirs in the examples talked about today with Prado and Lake Mendocino, where the main objective is, trying to make water more available, right? To have more water supply resilience and water supply reliability. However, there are other FIRO pilots, for example, Oroville and Yuba Feather, or on the Yuba Feather system, Oroville and New Bullards Bar, where the actual main point of the FIRO exercise is to improve the flood risk management capacity. When we move up to the northwest, again, it's not really water supply is the main driver. Now it's about timing for either hydropower or ecological benefits to species of fish or other things. So there's, FIRO is really just about flexibility in the operations, whatever the constraints might be, whatever the objectives might be. And so whether it's, if it's, you're trying to couple it with managing the aquifer recharge, well, then there's, that can be taken into account when we're doing the viability assessment for a particular dam. Is that what are the objectives? What are we trying to improve in terms of operations at that reservoir? And that uncertainty goes into, what are the inputs to that, whether it's meteorological uncertainty in the forecast or stream flow forecast as well.
Yeah, Kerry, and this is a good segue into the next question that we have, because this question points to FIRO at present using the HEF stream flow prediction. And the question is, are there examples of forecasts coupled to other hydrologic models of predicting stream flow as information tool for FIRO. In other words, how does the uncertainty in meteorological forecast compare to uncertainty of streamflow prediction? And there's a lot of research that's being done on this topic, both at CW3 and also at ERTIC, actually, where at CW3 we're using the National Water Model, or as known as WRF Hydro, where WRF, the weather research forecast model, is being used as input into a hydrological module that is doing the streamflow predictions. And there's research that goes into looking at how forecast skill can better improve these streamflow predictions. And I think at ERTIC, there's also an effort going on there. I don't know, Kerry, if you want to highlight that.
Yes, there is, and I'll just say that there's research that's an active area of research. But I think in Patrick's presentation there, he showed the streamflow inflow, the inflow forecasts for from the RFC. Those were what he was using in terms of not just looking also at the the weather forecast of inbound atmospheric rivers and what might potentially hit his watershed, but he was also looking at the ensemble spread in the inflow forecasts. Patrick, did you want to touch on that?
Yeah, I mean, I think you said it pretty accurately. Looking at that spread of possible outcomes and even planning for above that spread is what we were actively doing in the district. Also, due to time constraints, I didn't want to, put every possible image in there. But beyond the GEFS model runs for IBT, we were also looking at the European model for IBT for some, I guess, comparison, along with a more focused model that CW3 is running, which is the WestWRF model. So we tried to kind of evaluate all three meteorologic models that were available to inform our decision making. And there was times when there was an agreement between, for example, the European and the American model. So those were the periods for which I was trying to communicate with folks about, why is that the case? So that's all part of what the water manager would have to take in terms of making a decision. Now, if there's disagreement amongst the models, I think the water manager would be, the smart move would be to take the most conservative approach, which is if there's one model that says it's wet and the other one's not, I think you have to take the assumption that it's going to be wet, for example. But that's part of the experience of trying to do this in real time, which is to figure out what you would do in those scenarios.
Yeah, so I think the key takeaway there, Patrick, is I believe that Lake Mendocino and other water control plans actually do explicitly state that they will use the inflow forecast from the California Nevada River Forecast Center, for example. However, it doesn't say that that's the only thing you can look at. And so, having more tools, more opinions, more options out there to be able to provide, to inform your decision making is really what we're aiming for here, is to increase the fidelity, increase the number of tools that are available to a water manager such as yourself to be able to look at and say, okay, if they are all agreeing, if all these different sources are agreeing, then I have a lot more confidence in that forecast. But when there's a lot of variability or spread in those in what they're saying, well then, like you said, you're most likely from a flood risk management agency perspective, the Corps of Engineers, we're going to be conservative in that, just because that's our mandate is to manage for flood.
Patrick, and thank you for your presentation. And Kerry, thank you for your comments. Megan, I'll hand it up to you now.
Thanks, Duncan. Okay, so we're going to take a short break. Let's plan to return in 8 minutes at 10:53, but we will launch our next presentation at 10:55. So coming up next, we have Wyatt Arnold and David Arate with DWR talking about what work is being done to identify FIRO-MAR opportunities and advance FIRO-MAR implementation. So enjoy your stretch break. See you in about 8 minutes. Okay, I'm gonna give everyone the 2-minute warning. And see if I can't get a little soundtrack going on for us in our 2 minutes. Make us feel like we're in the tropics. We return from our break.
As the perfume of the million flowers singing to the heart. Oh,
All right, we've got Wyatt. Are you with us, David?
there's a rainbow.
Awesome. Okay. Great. Fade out our Hawaiian tropic music. Okay. So here we go. Next up, as I mentioned, after our break, we are excited to have on board Wyatt Arnold and David Arate from California Department of Water Resources. So you can bring up your screen when you're ready. And I did see a number of other questions and comments come through in the chat over break. Really appreciate those. Duncan is doing an excellent job of organizing those on the back end. After we hear from David and Wyatt, we will then move into our panel discussion with whatever remaining time we have. And Duncan will bring in a lot of those interesting questions to all of the folks who you heard from already today. So when you're ready, David and Wyatt, please take it away.
Can everyone see my screen?
Looks great. Plus a laser.
Yeah. Okay, great. Thank you. All right. Good morning, everyone. Yeah, I'm David Arate, and I'll be presenting with my colleague Wyatt Arnold on some of the FIRO-MAR studies that the department has been working on these past few years, where FIRO-MAR is a part of these studies. And we'll focus mostly on the first study that we've just about completed, the Merced watershed study. This was a pilot or recon study on FIRO-MAR in general at the watershed scale. So just some purpose and goals of what this study was for those who maybe aren't too familiar with Merced study yet. We looked at this as a proof of concept. This is the first time the department was really studying FIRO-MAR at a watershed scale, really looking at all the different components of the watershed, how to model it. This is a modeling and planning study. Just trying to look at, demonstrate the viability of FIRO-MAR, different strategies of FIRO-MAR, and investigating climate vulnerability, FIRO-MAR concepts, stuff like that. So to that end, we have an integrated watershed modeling tool set that we've developed for the Merced watershed. Models runoff through the reservoirs to downstream flows, the groundwater, the recharge assessment and optimization, all these different areas of the watershed, really to do two things. One, assess the vulnerability of the watershed to climate change. So we ran a pretty large suite of climate scenarios through all these tools to assess how climate change can affect this watershed at these three sectors, primarily flood risk, water supply, and ecosystem. And then we ran a huge suite of FIRO-MAR adaptation strategies to really test out different types of FIRO-MAR implementation, different types of FIRO-MAR components, and see how those mitigate climate change effects and can help increase benefits to these three multi-sector areas. So, and then lastly, we were hoping this study would be a template for future studies and projects for us, for locals, for whoever, and it has become a template for our next studies that we're working on right now that we'll talk about a bit, which are the San Joaquin Basin watershed studies. So there's a little bit of background into the Merced watershed, for those maybe not familiar. This is the study area, the upper watershed here that drains into Lake McClure. And we also have a few smaller reservoirs, flood regulating reservoirs on some of the creeks within our watershed study area. About 860 miles of conveyance. We use the Merced irrigation conveyance system to move those floodwaters off of the rivers and creeks and distribute them through the agricultural fields for recharge. About 130,000 acres of agricultural land, primarily in the Merced subbasin and a little bit also in the Turlock subbasin. And for the purposes of our study, we had to make some simplifying assumptions. So we assumed all agricultural land was available for FIRO-MAR use. We have a tool called GRAT, a groundwater recharge assessment tool that tries to optimize the recharge based on crop, land, soil types. Lots of different information goes into that and tries to optimize. But one assumption we made is that all land is available to be able to use for FLOOD-MAR. How realistic is that? And we'll see as we get landowners, on board with FLOOD-MAR eventually. So for the FLOOD-MAR study, we looked at a wide range of scenarios broken down into what we call 3 implementation levels. First level was just using excess flows, just diverting water off the streams above some certain threshold. And we looked at 3 different scenarios within that. In our level 2s, we start to layer on reservoir reoperations, and we looked at 3 types of reoperations: FIRO, a recharge pool concept, which is drawing down the reservoir at a controlled rate and moving that water into the ground, and then a hybrid, which does both the FIRO and the recharge pool together. And then in our level 3, we layer on top of that infrastructure improvements, things like larger turnout capacities to fields, be a little more efficient in getting water onto the fields. If there's commands bottlenecks that were identified in the system, try to open those up. So for the purpose of the study, we're just going to focus on the FIRO scenario from our level 3 version, but we do have all these other scenarios modeled results for these as well. We'll just focus on that today. And when we modeled all this, we used 100 years of continuous hydrology, simulated 1900 to 1999. So we have long-term average results. We can look at specific events. We can look at the results lots of different ways. For this study, or I'm sorry, for this presentation, we're just going to look at one specific event to just kind of highlight the FIRO ops that we study. So first we'll look at reservoir vulnerability. So on the top here, we have the storage curve for Lake McClure. The black line is the rule curve during the flood period. The blue solid line is the storage during this simulated event. So it was the 1956 event that we're looking at specifically. So this is the simulated storage, and here's the simulated inflow for that event. So in this event, it does encroach into the flood space of the reservoir. So down here we have a flow in the river downstream of Crocker-Huffman Dam, which is kind of the last regulating reservoir in the system before it goes into the Merced River. So we're on a flood event. So peak flow for this event is about 6,000 CFS until it returns back to the rule curve. There's some snowmelt operations that happen here, so we have some elevated flows that happen. For current climate, Lake McClure does have very good flood control. They've never really gone above 6,000 to 7,000 CFS, which is about the channel capacity of the Merced River. Now looking at one of our climate scenarios from this study. So this was 3 degrees of warming and about plus 10% mean precipitation increase. So the red is this future storage now. For this event, we came in a little bit lower in storage, but there was a lot more inflow in this event, driving storage up to essentially the top of the dam, pushing the reservoir into emergency release operations, where we have an emergency release of about 42,000 CFS. It's a much longer event, so we're holding, once we are able to bring storage back down, the reservoir is still holding at that 6,000 for a much longer period of time, about an extra month. As we get past the event into the spring and summer, we see another effect here. So we have an extreme flood, but then we also see less carryover storage. We have less inflow in the spring and summer months due to climate change, more demand, warmer temperatures, more demand from the crops. So we actually end up with lower carryover storage heading into the summer for this flood event. So for the FIRO-MAR operation that we modeled in this study, these are kind of just the highlights of what we looked at. First thing was increasing the flood release capacity. Typically, they try to hold flood releases at 6,000. That's the channel capacity of Merced River. We have a diversion capacity for the Merced Irrigation District's main canal of 1,900 CFS. So we increase essentially the flood releases up to 7,900 CFS. If there's capacity in the canal system, we can peel off up to 1,900 and keep flows downstream still at that 6,000. We used a 5-day forecast period for this study. It was a perfect forecast. We didn't really know how to incorporate any kind of uncertainty at the time, so we used a perfect forecast. But Wyatt's going to later on in this presentation talk about ways we've improved on not using a perfect forecast. We incorporated a pre-release ahead of this ahead of large forecast inflows. So if there's a forecast inflow that pushes the reservoir near the top of the dam, we've incorporated a pre-release that can pre-release up to the 79 to try to open up a little bit more flood space. We incorporated this 50,000 acre-foot FIRO-MAR buffer zone here, where we try to let the reservoir encroach about up to 50,000 acre-feet into the reservoir's flood space. Try to meter those flows out at this up to this 1900 CFS rate to really try to hold some water in the reservoir, meter it out at a slower rate that we can divert as much of it as possible for FLOOD-MAR recharge, while still protecting minimum in-stream flow requirements, any kind of flow requirements downstream in the Merced River. We also increased the minimum flow releases. We had some work done on the in-stream flow for fish habitat. So we've increased those minimum flow releases to try to get some more ecosystem benefits in the in-stream habitat. And then lastly, as we get towards the end of the flood season, if we still have water banked in this FIRO-MAR zone, when we get towards the end of the flood event, end of the FIRO-MAR, FLOOD-MAR period, we take that banked water and turn it into what we call an eco pool account. That's water we've banked, and we try to use it for ecosystem purposes. So a few things we use it for are shorebird releases. We designated some fields that are good for shorebird habitat where water can pond a few inches for a few weeks at a time. So we'll release some water, direct it to those areas, create some shorebird habitat. We'll do off-channel habitat inundation releases. We'll kind of release at a higher peak flow and then draw it down slowly, do some off-channel habitat inundation, and then a spring pulse release that happens after that for an out migration pulse. So let's look at some results then. So we'll focus on the future climate scenario. We had that huge inflow that pushed our reservoir up to the top of flood, a large peak inflow of 42,000. So when we look at the FIRO-MAR strategy implemented on top of this, first thing we see is we have that pre-release that kicks in. It forecasts this huge inflow coming in. We're able to pre-release a little bit before, while we're still in the conservation space, a few days early, and it opens up just enough extra flood space that we can absorb not quite the entire inflow, but most of it. And for most of this time, we're releasing at 7,900 CFS instead of 6,000, so we're evacuating the reservoir a little bit faster. So we're able to decrease the peak flow from 42,000 down to 15,600. Not quite back down to the channel capacity, but still a very large flood risk reduction. As we get back into the FIRO space here, you can see our outflows start to dial back a little bit. We try to hold the reservoir within this FIRO space here as we're getting towards the end of the event in our FLOOD-MAR season. We're riding pretty much right on top of our FIRO space. So all this water will then be turned into our eco pool account so that we can do some eco pool actions. So we do a shorebird release here in March. We do that off-channel habitat inundation release in April, and then that spring pulse release in May. And essentially, we're able to get back to the same storage as we had in the baseline. So we got flood risk reduction. We were able to do, for this event, about 265,000 acre-feet of applied FLOOD-MAR recharge through MID's conveyance network and agricultural fields. And we were able to do all these ecosystem actions. So this is where we really focus on that multi-benefit, multi-sector FIRO-MAR application. So I just focused on a single event just to kind of highlight the FIRO-MAR actions. This is a little more broader select results from our study, really looking at those three water sectors: flood risk, water supply, and it's really surface water and groundwater that we're looking at, and then ecosystem. Red is declining performance, so we look at our current baseline and one of our future scenarios, and then adaptation performance across a couple of the FLOOD-MAR strategies. I'm not going to go through all these results. There's a lot of different ones here, But this is kind of some of the stuff that we're generating out of this study is how is FLEDMAR and FIRO-MAR doing? What's the performance of it compared to our baseline and our climate vulnerability results? And a lot of this information will be in our reports that'll be on our website soon. So we've wrapped up the Merced study. Essentially, we're now moving on to these San Joaquin Basin watershed studies, where we're expanding from the Merced watershed to the other tributary watersheds in the basin. So we have Upper San Joaquin, Tuolumne, Stanislaus, and Calaveras. We're modeling all these simultaneously together. We've done some updates from what we did in the Merced study. We're using some new hydrology. Compared to what we used in the Merced study, we're using the weather generator to perturb that hydrology for the climate change scenarios. And this next part is really important. This is why it's going to focus on here in a minute. Is we use the perfect foresight in the Merced study. We're now using this forecast error model to try to introduce some uncertainty into our forecasts. And then we're updating a lot of the FIRO-MAR scenarios based on what we've learned from the Merced study, based on the new hydrology, this new error model. We're trying to be consistent through the watersheds, but each reservoir kind of has its own unique characteristics. So we're adapting the FIRO-MAR ops to each reservoir. And then we're incorporating those ecosystem operations again and tweaking those a little bit more based on some new information that we've been developing. So I'm going to pause here and hand it over to Wyatt for the next few slides.
Thanks, dude. 1 second while I get my PowerPoint up. Okay. Yeah, so as David said, this is the expanded study area, which incorporates 5 different watershed study areas and 7 reservoirs where we will implement this FIRO-MAR operation in the MTA scenario, the middle.
May I interrupt you quickly? Sorry, you're in presenter mode. We can't see the full screen. There we go. Thank you.
It doesn't tell you. Okay, so yeah, 7 reservoirs across these 5 watersheds. In the Upper San Joaquin, we have Eastman Lake, Hensley Lake, and Millerton. In Merced, as David was showing, we have Lake McClure, Tuolumne, New Don Pedro Reservoir, perhaps the largest, and well, maybe the largest flood risk, but I think Stanislaus, New Melones Reservoir might be a little bit larger, and New Hogan Lake on the Calaveras. And as David said, we're doing a 100-year period of analysis on a continuous simulation of daily meteorology based on a historical observed record, but perturbed with that weather generator for a whole range of climate change conditions, changes in average precip, changes in temperature, and also changes in extreme precipitation associated with thermodynamic scaling of these big events. Now, if we want to incorporate forecast uncertainty, we need a forecast to simulate. And that actually becomes a particularly challenging thing to create when you're doing a virtual, simulation study. Really, I think, the first option, which would be the state-of-the-art option, would be to use a reanalysis hindcast. However, it's only available at a few locations currently, that it's been prepared for other FIRO viability assessments at a few other locations in California. If we wanted to create a new one, it's very expensive to run. Not only that, it tends to have a pretty limited time coverage, relative to the 100-year period of analysis that we would like to, assess performance over, right? To get that long-term average benefit, knowing, how much variability is in California's climate, the longer period of record you can simulate, the better. So 1981 may be a little bit too short, fewer events to simulate. The other option that we discovered, really trying to think through, okay, how are we going to do this? We didn't have the solution. We looked outwards to other experts out there. Of course, there's been quite a lot of research in the synthetic forecast area. Recently, I think there's been some really great advancements. We looked to Scott Steinschneider and Zach Rodur at Cornell. They've been also, they were the ones actually that, especially Scott, who developed the weather generator that we're using. They're also doing research into generating synthetic forecasts. The advantage of a synthetic forecast is that it's cheap to run. And it can basically cover any time period you like, any hydrology you like, because you're generating it in that synthetic space. The downside is that it's statistical. So it may be impacted by, that whatever assumption, whatever limited record you have to base that model on, those biases will carry over into your synthetic forecast. And depending on how long your record is, you may only have a handful of major events to kind of capture the quality of forecast on those events. So we chose, yes, to do synthetic forecast. We decided to develop a synthetic forecast with a model of observed air from the short range ensemble, which actually incorporates, for some of these reservoirs, basically they're upstream impairments that can affect, those operations can affect the inflow to the larger downstream reservoir at the watershed outlet. So we use the ensemble that incorporates, those published operational ensembles going back to 2013 are available, and that's what we used to build a model of air. An important note there is that over time that ensemble forecast skill may have actually improved, and there is some understanding that yes, it did improve for certain locations over time. So it's a non-stationary. In terms of skill, it itself is a non-stationary record of forecasts, but we treat it as a stationary sample. So that's actually, I'll just say that's one of the major benefits of using the reanalysis signcast, is that you're basically using the latest and greatest version of a climate model and its skill to project back onto some historical record of meteorology. And so you have this kind of constant stationary skill that you can evaluate in your planning study. Okay, so just looking at Don Pedro, here's that California Nevada River Forecast Center short range ensemble. The green line is the ensemble mean. That's what we're actually using as the air marker. Right, so the blue is the actual observed. So this is 5 days out of from that New Year's storm on 2023, December 2022, January 1st, 2023. You can see there's a significant air in the 5-day, and then here's 1 day lead coming up just ahead of the storm. There's still under forecasted, but perhaps not as bad. Okay, so that we're basically going to look at all those airs across that 2013 to the recent, essentially through 2023, and we're actually limiting our synthetic forecast model to the November through March period. So we're not really looking at forecast uncertainty in the snow melt or the spring period. Part of that's because we only do FIRO-ops in the planning models in the study through March, November through March. So what are the features essentially of this synthetic forecast model? Really, there are 4 key things that the forecast model incorporates, forecast air model incorporates. One is mean bias, conditional mean bias. So what that means is, well, you would expect that the forecast has some dependency on the flow and the observations. But what you would see, and this is in the 7-day lead, that as the observations grow, these are instantaneous, flow observed flow 7 days ahead against the observed forecast 7 days ahead. So the CNRFC's ensemble mean. That's the y-axis at 7 days. And so what you see is that as the observations grow, essentially as the events get bigger, well, the forecasts start to drop off. So that essentially shows that there's a consistent or conditional mean bias in the larger events. They tend to be under forecast. The other key feature that we're incorporating here, again on the right-hand plot, is the heteroscedasticity for the 7-day lead. And what does that mean? That means that as the forecast value increases, so does the range, essentially the variance of the error itself with that forecast. So the errors get bigger as the events get bigger. And then the other two, these 3 and 4 are actually under this third check mark here, correlation in time and across leads. And so what we're dealing with here is, your forecast of the 1 day and your forecast of the 2 day are correlated with each other. That's correlation in time. That's correlation across leads. Correlation in time is where you release a forecast 1 day for the lead 1. You step to the next day, you release another lead 1 forecast. Those two are going to be correlated. So that's correlation in time. So both of those correlations of errors are incorporated in this synthetic error model. And the fourth is that we don't assume a Gaussian distribution of the residual errors. And that becomes really important because if you look at the residuals, it doesn't look normal, right? So that is an important component to correctly sampling sort of the residuals of the error. For more background, again, you can look at the research produced by Scott and Zach that's been published recently. We're using sort of an updated version of this, but it explains, all the background and sort of the logic that goes into this type of synthetic error model. So I'll just list a few benefits, kind of stepping out of the technical morass. The benefits that we see of using the synthetic forecast error model over a perfect forecast assumption is, well, first, we would interpret that what we've gotten so far for all of these reservoirs that we're going to model, we have an acceptable forecast error reproduction. 2, we see it as an improvement. We can't really share results quite yet. We're not ready for that. But so far in the limited assessments we've done, it seems to be a definite improvement over using perfect foresight assumption. Essentially, it limits under overestimation of the flood and water supply impacts. We need to make sure to caveat that this is a planning tool for estimating the benefits of FIRO-MAR in this multi-sectoral complex system scale study. So, ideally, you would use a much more refined, state-of-the-art reanalysis, et cetera, to do these FIRO operational assessments. But again, we have many models that we're integrating here. We're looking across many sectors. We have many watersheds, and we're simulating over a very long period of time with climate change. So that amount of complexity, in a way, kind of demands a more simplistic representation, perhaps, to just make it feasible and practical. But as always, this is essentially our first iteration of this. There's plenty more room for improvement in understanding how to better represent forecast error in these planning studies. That's what I got.
Thank you, David and Wyatt. There is one question that I think you've addressed, Wyatt, but maybe you can give us the highlights. What does synthetic forecast mean? What is the time scale of these forecasts, and what is the range of uncertainty in the forecast? And I think the question was asked before you got into those slides that addressed it, but maybe you can give us a couple highlights on that.
Well, a synthetic forecast means, okay, so I'll just step back one more time through this. In our case, we're looking at a real forecast, and we're trying to build a model of how wrong that forecast is. So that actually establishes the range of how uncertain our synthetic forecast is going to be. We're trying to model that exactly as possible. Once we have a model of the air, essentially the uncertainty in the forecast, we can apply that air to any record of inflow. So we're basically superimposing air on top of some other realization of inflow that has been modeled. That allows us to be quite flexible, right? Because we have these, the weather generator produces synthetic time series of temperature and precipitation. That's a whole nother story. We take those time series of temperature and precipitation, we simulate them through a hydrologic model, SAC-SMA. That gives us time series of inflow to the reservoirs. Now we can take our model of air, and every day for each of those leads, 1 through 7 days, we can apply that air on top of that inflow that we've modeled. And we take that, combined time series, and we use that as the input to the FIRO policy. And the FIRO policy basically says, okay, what's the forecast? What's my storage? And makes a decision. It's obviously a little more, the FIRO policy itself can be really, that in itself is a question of how do you design that? We're less, I say, sophisticated on how we design that. We use a lot of heuristics to get at that. There are other ways that are more optimization driven ways that we don't do because they're not feasible for us. But at the least, we've been able to have this sort of synthetic version of air informing the FIRO decisions in the model. And then as far as like, how do you, in a sentence, describe the range of air that we have? And it's not possible. I mean, you kind of have to look at each lead. Each lead has its own forecast bias, its own variance in that forecast bias. And that's how you would quantitatively describe it. Qualitatively, it's an uncertain forecast. It has air, and it's very bad. Sometimes that forecast air can be very bad. Sometimes it's good. So I guess that's qualitatively how I've just put it.
Yeah, thanks, Wyatt. Yeah, I know this is a emerging field of research. These data sets are coming online through university collaborations, and graduate students and their PhDs are doing great work, and we're trying to incorporate the state of the art in our work. So thanks for highlighting that. A question for David has to do with the availability of the reports, both for the Merced and the Seven Basin study. I think you mentioned that these are going to be available very soon.
Yeah, for the Merced study, we're in the process of wrapping up the documentation and releasing a few reports on our website over the next couple months. The first one that's coming out, I'd say maybe in about 2 or 3 weeks, is the analytical tool integration. So it goes into all the models that we use in the study, how they're modified, used, integrated with other models. The next one after that, which is probably about a month or so out, is the baseline vulnerability results for the Merced water study. And then the last one will be the FIRO-MAR adaptation. So we're trying to get them out as soon as possible. I'd say over the next 2, maybe 3 months, they'll be posted to our website. For the watershed studies, we're still very much working on them right now. As Wyatt said, we're working on the modeling. Our due date to have them completed and the documentation completed is June of next year.
Thank you, David. Let's switch to questions that are more specific to FIRO testing and FIRO operations. One question is about which reservoirs is FIRO being planned at in terms of testing, and I can start with that, and then others can pitch in, especially if Kerry is on the line. So the US Army Corps FIRO pilot was Lake Mendocino. So there was a lot of learning that occurred from Lake Mendocino. And from that learning, that is being expanded to other sites. So there was Prado Dam, and we heard from Adam about that. And following that, there's FIRO testing going on at Orville and New Barrels Bar. In addition to that, having done FIRO at Lake Mendocino and the Russian River, now FIRO is also starting at Lake Sonoma, which is also on the Russian River, and Patrick talked about that. And also analogous to that, in the Santana, we're starting to do FIRO at Seven Oaks. Outside of California, FIRO is starting at Howard Hansen Dam in the Green River, which is in Washington State, near the Tacoma, Seattle area. In the future, Kerry touched on the national pathfinder, the national expansion of FIRO that is largely being driven by the screening process. And some of those project sites have been identified, but some have not, especially the ones that are related to expansion for weather systems that are not driven by atmospheric rivers. So now the next frontier for FIRO is going to be, how do we improve forecast skill for non-atmospheric river related storms? And once we do that, or are able to characterize the forecast skill, is that forecast skill sufficient to implement FIRO at sites where AR storms are not a major component of the precipitation climatology of that watershed? I'd like to give Kerry an opportunity to speak if he's able. If not, we can move on to the next question.
Yeah, thanks, Duncan. And I apologize in advance for any extraneous noise. I had to transit to the airport, so I'm actually in the airport right now. So if you hear an announcement, I'm sorry about that. But Duncan, you did a good job of summarizing really what phase 3, what we know so far about sites. I mentioned the Willamette system before. We've been in conversations and have looked at a few sites in the Northeast as well as in the Southeast. And so there are other potential sites around. We have not identified all of those yet, but we will, as Duncan, you mentioned, we will be using the screening process to help drive that. Congress actually authorized the Corps to put together a list, a prioritization list of water control manual updates, not necessarily only based on FIRO, although FIRO is a component of that. Some of that has to do with just age of the watershed, the water control manuals themselves might be out of date for various reasons, not just because of age, but because of changes that have happened in the watersheds. And so that effort is ongoing right now to create that prioritization list. And so that will also help inform where we take FIRO next. But it will be much like we did with selecting our pilots, we will use the screening process, which we've developed to help identify which are the best next candidates for FIRO. Over.
Yeah, thank you, Kerry. I'm gonna move to a question on the results from the Lake Mendocino final viability assessment. So this question is for you, Patrick, and it references the approximately 20% additional water supply for the water year when the FIRO paradigm was first tested. Can you describe how that was achieved?
Sure. I think you're referencing water year 2020, correct? For that 20% increase in storage?
Yes.
Yeah, I don't have the plots ready to go for that water year, but it was similar to the plots that I showed in my presentation for earlier this year when we were storing water between the end of January into February. A lot of the forecasts at that time in 2020 pointed to minimal reservoir inflow, minimal to no atmospheric rivers approaching the west coast of California. So we were using similar tools in 2020 to inform our reservoir release decision making at that time. I think the only difference between 2020 and this water year was I don't think that we had the same lines of communication with the subject matter experts that we have now versus then. Although at that time, interpreting the dry weather forecast was a lot easier than, say, interpreting wet weather forecasts and differences in outputs between weather models. I think in the more recent years, that has forced us to establish those lines of communications when trying to interpret those type of products. But in 2020, we had less difficulty in interpreting the dry weather forecast. So it wasn't too difficult in 2020 to make the decision to retain the water that water year.
Excellent, thank you, Patrick. And a follow-up on that, one question is, are there any changes to magnitude of releases when space needs to be evacuated for a forecasted storm? And I think you've alluded to this in your traces, but maybe you can explain a little bit more detail how that is done in real time.
Sure. Well, I think it has to do with how much lead time you have for an event and the magnitude of the event. You know, Lake Mendocino, we have 11,600 acre feet of storage that is reserved for forecast and informed reservoir operations. So if you're trying to evacuate that amount of space, you know, 5 or 6 days in advance, then you can do that with a release rate that's relatively low. If for some reason, you know, the forecast of the storm were to kind of appear in our products on short notice, then we would have to adjust our release rate accordingly, and that is to increase the release rate. It's important to note that the 11,600 acre feet defined for FIRO at Lake Mendocino was not some random number that was generated. That was the result of the numerical analyses that were done prior to real-time implementation to figure out what space could be, you know, managed with, you know, long-term or even short-term notice. The 11,600 acre feet could actually be released over a period of 1 to 2 days if it was absolutely needed, but that's not something we would like to do. We would like to try to, you know, make our release well in advance of that. So it's important to note that the space defined for FIRO, you really have to kind of do some numerical analyses first to figure out what that space is. It's not some random number that gets put on a page.
Thank you, Patrick. One of the FIRO benefits is the enhancement of environmental conditions that are related to the watershed. And there's a question related to that. Can anyone speak more to the reservoirs that are using FIRO to create more water for the environment rather than water supply for humans? Are there any changes to implementation being between intended uses? So maybe Adam can highlight some of that, and then Patrick, and also David from a modeling perspective.
Sure, I'd be happy to jump in. Just a little bit of background about Prado Dam. The base flows of the Santa Ana River coming from the upper watershed flowing through Prado Dam historically are made up of wastewater discharges by cities in the upper watershed. And that wastewater has declined over time because of more recycling. That water is more valuable, so the upstream agencies are doing a lot more recycling. And so base flows have gone down considerably since the early 2000s. And so whereas when we were looking at water conservation back in the 2000s, too much water was a concern. Well, now with the base flows going down so low, temperatures rising, more variability in precipitation, there's concern that there may not be enough water for the habitat behind Prado Dam. And so that's where FIRO really jumps in and actually helps to benefit the habitat in doing periodic flood irrigation. Like this year, for example, you know, we've had several dry years, not much water behind the dam. Now this year we've got a lot of water. So what we're seeing FIRO helping is holding water at high elevation, providing for more flood irrigation during the wet periods that can help sustain that habitat in the intervening dry periods. And so I think that's really one of the biggest environmental benefits that we're seeing at Prado Dam.
And Patrick, could you speak to the fisheries? I know it's not your expertise, but you've participated in the conversations, and maybe you can bring that here.
Sure. You're right, I'm not a fisheries expert, but one thing I do know from my conversations with the fishery experts is they like colder water, released particularly from Lake Sonoma, where we have a hatchery at our facility. So water released out of the lake is diverted to the hatchery at Lake Sonoma. And with the higher pool that we're retaining right now at Lake Sonoma, that will allow for colder water this year and for years to come if we do have future drought conditions. So being able to store more water in Lake Mendocino or Lake Sonoma, that higher column of water allows for colder water. You can imagine if you have a shorter column of water, that sunlight can penetrate pretty much down to the bottom of that column of water, and you have basically warm water being released out of the reservoir. Now that we have a larger column of water, that overall temperature is colder, and that water is beneficial for fish. That's probably the crudest explanation I can provide with respect to fisheries, but that's what I've learned in recent times for Lake Sonoma.
Maybe a small follow-up on that, Patrick. Can you speak a little bit to the how that comes into the water control manual update?
Sure. I mean, I think, when you write a water control manual, the primary objective is to develop rules for flood risk management to ensure that we make reservoir releases that don't harm communities downstream. This is kind of an ancillary benefit, I'd say, in terms of being able to provide that colder water flows to our fish hatchery. So it's something that, I think the Corps can consider as we evaluate alternatives for potential inclusion into a water control manual. But at the end of the day, our mission is flood risk management, and that's going to be our utmost priority as we update these water control manuals.
Okay, thanks, Patrick. And David, you spoke about the modeling aspects of this. Can you elaborate a little bit on how what was considered in building the boundaries and parameters of the modeling aspects of environmental impacts in your study?
Yeah, so from the start, when we started looking at FIRO-MAR, we wanted to really focus on the three sectors simultaneously: water supply, eco, and flood. And before the reservoir re-ops, there wasn't much that could be done in just the high flow diversion for ecosystem, especially in stream. That focused mostly on the recharge. But when we got to the FIRO ops and we started, with that FIRO space and holding that water, and we saw through a lot of preliminary model runs, we would, by the end of the kind of FIRO-MAR season, still end up with a lot of banked water that was just going into water supply, but we already did a lot of recharge during the event as well. So we started thinking, well, this is something that could be really beneficial for ecosystem. On the Merced, there wasn't much springtime ecosystem ops. They mostly just have, their minimum stream flow requirements and a fall fishery flow. So we worked, I think, with UC Davis, one of our consultants, to see, there's this concept of functional flows for fish, and we incorporated a lot of that work to try to design, what would be good for fish in stream and off channel. It's not the end of the analysis, it's just kind of a demonstration based on what we could collect so far. But yeah, we started putting those pieces together. Shorebird habitat was another thing that was suggested, that's something we could do if we've got some of that banked water. It doesn't take much water to inundate a few hundred acres of land for shorebird. So we just started putting all the pieces together. Once we bank that water heading in towards the end of the season, depending on how much we banked, And one part I forgot to mention is snowmelt release also got incorporated to that. A lot of these reservoirs do have snowmelt operations in the San Joaquin Basin. So we would look at kind of the forecasted snowmelt ops and incorporate that into that eco pool account, as we called it. And based on how much water there was, and based on some of the guidance from our consultants about what would be needed to do some kind of minimal amount of inundation, some amounts of in-stream flow habitat, what would be needed to the shorebird, we kind of set some thresholds within that eco pool account. If we surpass this threshold, we can do this much eco operations. If we surpass more threshold, we can do more eco operations. So in the example I showed, we basically were at that full 50,000 acre foot. So we were able to do all the eco operations, shorebird, off-channel habitat, spring releases, and at a pretty high rate of flow, kind of targeting a good amount of flow. So we're carrying those concepts over into the watershed studies, doing some additional analysis. Different watersheds there already have some existing operations for ecosystem flows in the spring. So we're trying to figure out how we can use FIRO to maybe add more resilience to those operations, not dip into water supply as much, or bolster them even more. So a lot of that work's still in progress. But that was kind of in general how we looked at using FIRO to help with these ecosystem flows and operations.
Thanks, David. And I'll follow up with you, David, on this topic here, and also I'll ask Carrie to pitch in as well, and it has to do with stakeholder engagement, which is an important aspect of our work. Carrie had a slide on it. In particular to the Merced and the San Joaquin watersheds, how have the stakeholders responded to your study? What kind of feedback have you received?
So in the Merced study, the feedback and response has been great. When we first approached Merced Irrigation District, they were interested but cautious to what DDR was going to do. But as we worked with them, we took all their input, we showed them what we were doing along the way, and now they've started working on their own FIRO-MAR projects. They've started working on permits and looking into FIRO-MAR, using a lot of the information we generated from our study to start working on their own pilots. So we think that's great. That's really what we were hoping for, is from our studies and our engagement to get locals, really energized into the concept of FIRO-MAR. And it has spread to other watersheds. Since we were working on the watershed studies, we were contacted even before we even started from other watersheds that had heard about the Merced study, wanted to know, what we could do for their watershed. So we've been working with a lot of stakeholders, a lot of irrigation districts, flood managers, water supply managers, ecosystem folks on all the watersheds, showing them what we've done on Merced, what our concepts are, keeping them engaged throughout our process. And the feedback's been great. They're all very interested. They really want to see our results. They're very interested in our models. Most of these districts don't have much modeling capability themselves. They're interested in everything we're generating. It's what we hope for sure, to get a lot of interest and a lot of engagement, and they're essentially our partners on these studies.
Thanks, David. And Carrie, the same for you. You sit on many steering committees related to the FIRO sites. There's 5 projects. Each project meets quarterly with the steering committee. Can you tell us a little bit about that engagement and the feedback that you get from stakeholders?
Yeah, sure, Duncan. And again, I apologize if there's any announcements. There's several flights boarding right around me. So the main point here is that I had on my slide is that collaboration is the key to success with FIRO. Making sure that we have appropriate level and appropriate agencies represented on those steering committees is really vital to making sure that as we look at changing the operation there, but incorporating FIRO into the water management operations there, all of the relevant stakeholders need to be represented so that we can go forward with a viability assessment that covers all the bases really. And then also then therefore carries the backing of all of the participants on the steering committee. So when we produce our viability assessment reports, they are not a core report. It's actually a report of the steering committee. And so it carries the weight and the backing of all of those participating agencies. And therefore it's hard to say what perspective what wasn't represented in that viability assessment. And so it's not just any one particular agency that's driving the move towards incorporating that. It's being assessed from all of the regulatory, water supply, flood risk management, hydropower, or whatever the other interests might be at that particular site. And so that's just really key. And so we carefully form those steering committees to make sure that we've got appropriate levels of individuals who can speak for those agencies represented on that committee, and that we have all the needed agencies on it. Over.
Thank you, Kerry. So making a full circle here, we started speaking about the meteorological aspects and atmospheric rivers. So I'm going to turn to our meteorologist here, Chad, with a few questions that have lingered from your presentation. And the first has to do with forecast skill. And essentially, how good are these models in predicting the occurrence and strength of AR events, and how far into the future can ARs be predicted? And what comes to mind is the analysis that you and your colleagues have just completed on the AR2 and greater for events that date back to, the exact dates. Maybe you can elaborate on that a little bit.
That's a great question. It's also a very subjective question. Different users need different things from a forecast. And I think Patrick made a great point where the collaboration that we have together is really, it's ideal in this scenario where we're bouncing ideas off of each other, and also questions that he has about the forecast I can give him, but every user needs something different. This past water year was challenging for many different reasons. We have that the atmospheric river landfall tool that Patrick showed, and the plume diagrams that give you information about different storms that are going to make landfall in California. And we've done analyses with that forecast product and identified that we typically get, if we're looking at a probability threshold, 75% probability that an atmospheric river is going to make landfall, we typically get about 5 days worth of lead time, which is generally good for reservoir operations, especially in a watershed like Lake Mendocino or the Russian River watershed. An anecdote that I will say is that New Year's event that has been discussed in this workshop a little bit. We had essentially 2 weeks worth of lead time on that. We knew something was coming 2 weeks in advance. We knew an impactful event was going to show up within 2 weeks, and we had that lead time to really sit and diagnose that forecast and identify what the challenges were going to be. Unfortunately, that was also a very bad precipitation forecast. That was the event that we knew the event was happening. It did happen, but as it was happening, there was minor details within that forecast that led to poor precipitation forecasts, especially around the Sacramento area, where there were major under forecasts within all the models. Everything under predicted the precipitation especially around the Casumnes or Casumnes, depending on how you want to pronounce it, which is where we saw a levee break, which is again something that you can't really predict. That's an engineering or structural failure that is really hard. You can't predict that's going to happen. But that's just an anecdote that, hey, that forecast was really well done if you just look at the atmospheric river conditions, but there's details within that forecast that you have to really try to identify beforehand that sometimes doesn't really doesn't necessarily happen, and that's a really good example. And every user needs something different, whether it's high intensity precipitation, whether it's long duration, whether you're forecasting for, say, New Bullards Bar in Oroville, where there's a confluence downstream, or it's the Russian River where, you know, they're operating a reservoir that just that doesn't necessarily have to deal with a confluence. So there's forecast challenges, but to answer that question, we generally get pretty confident forecasts within 5 days. And we're typically working on improving that day in and day out. And I'll pass that back to you, Duncan.
Thanks, Chad. And we're close to the end of our time here, but I do want to ask Carrie this question, because we got one question, Carrie, that I think you can address very well with reference to some of the details of the screening process. And the question is, thinking at a statewide level, is there currently, or has there been any thought given to the Central Valley, the San Joaquin Valley wide assessment to prioritize studies, work, and resources to address managing flood risks, ecosystems, and water supply, coupled with increasing MAR potential very wide? And if not, how are dams reservoirs elected to move forward with FIRO viability assessment? So, Carrie, maybe you can handle the FIRO part of that question, and then maybe David or Wyatt could fill in the gaps with the MAR part.
Okay, just real briefly, again, we will use the screening process in that, and we're going to use that on all the course portfolio of dams. So whatever in the Central Valley or core dams, then we will be using that process on them. Other than that, we really, that's how we're going to move forward on that in terms of our prioritization.
Okay, thanks, Carrie. And this screening process is a very thorough process that uses questionnaires that are being sent to the water managers to essentially gauge the capability of the dam, how it's operated, and also the watershed, the environmental considerations, the data that is available to assess forecast skill and so on, to assess whether a viability assessment could be the next step at that particular site. And David, Wyatt, I don't know who wants to handle this on the MAR side. Is there something analogous to a screening process for flood MAR?
Not at the moment, I guess. I think from DVAR's perspective, we're just working on these studies to demonstrate the viability of flood MAR. I don't know if Jenny Marr is available. I think she's been looking into some pilot type projects of MAR. And if there's been maybe a screening process there, I'm not sure if Jenny's available to maybe add some more feedback to this. Just from this watershed studies perspective, we've just been focused on the Central Valley right now and on the San Joaquin specifically. Do you want to add more, Wyatt? Sorry.
I was just going to comment that you could interpret, the department's watershed studies in collaboration with all the local agencies as a screening in itself. I mean, we are essentially studying to see where the benefits could be significant. for MAR and FIRO coming together. That could itself be used as a way to establish some implementation plan.
Yeah,
Jen?
this is Jenny. I was gonna pretty much echo what Wyatt said, that I think once the watershed studies are completed, the information that comes out of them will be able to help provide a wide scale basin-wide assessment of potential future studies, additional work, implementation, and help inform hopefully some prioritization within that.
Thank you for the comments there. I want to thank everyone for attending and the excellent questions. And also I want to thank the excellent speakers here for spending the time to prepare the material, but also the delivery here was excellent. And Megan, also thank you for helping to facilitate this. It's amazing to see how the intersections of FIRO and FLOOD-MAR are coming together with each conversation that we have on this, and I look forward to future conversations along this topic. Megan, are there any further announcements? Do you want to take it from here?
Thanks, Duncan. I just posted a link in the chat to the FLOOD-MAR Hub website, so today's recording will be shared up there. And when you exit, you'll be prompted with a quick survey that says, what do you want to hear more about? And what could we bring to a LunchMAR session or the FLOOD-MAR Forum later this year? We're looking at November 7th and 8th. So details for all of that coming next week. Thank you so much. That's it. Enjoy your lunch.
Bye.
Thank you.